Thank you, Mr. O'Kane. Welcome to the FE review session on soil mechanics, foundations, or commonly referred to as geotechnical engineering. What I've got is I've got two separate documents I've handed out. One, we'll go over both of them on the board up here briefly. One is a 9-page document I put together. I refer to as everything you might want to know about geotech. A lot of the good things, the kinds of things you're going to see on the FE review from a geotech standpoint. You're not going to be designing shoulder pile laying walls and deep pile foundations and all that kind of stuff on the FE exam. It's going to be back to the basics of soil mechanics type stuff, simple bearing capacities and things of that nature. And then I've also got the pages out of the review manual, the reference manual, and we'll go over it as well. They use some different symbology, so I want to make sure you guys are up to speed on the changes with that. And so we'll run through both of these documents to start off with. Once we get through that, then I have a large number of problems up here. I probably have 40 problems all told on geotech, and we don't have to do them all. We'll run through this one initial set I have. It's like 20 problems, but that gives you a good indication of the kind of problems you're going to see. And then if there's other problems that you want to see of a particular nature, I can find some others in my book, or I can just keep working problems until everybody gets tired of hearing me work problems on the board. So we'll get started. First document we're going to look at is the one that's handwritten on the engineering, Marshall Engineering graph paper. And here again, these are the things I think you need to know for this level of test. Some things I've got like at the beginning here, just memorize. If you memorize those basic equations at the top, you will be able to move much quicker when you go to do this testing if you have to do some weight volume relationships. One of the biggest ones that you don't find written in manuals and things of that nature is the one for the specific gravity times the moisture content equals the saturation times void ratio. If you've got that one, just about any other equation, you can get to where you need to get to find the other terms. We've got dry unit weight. I calculated two different methodologies, the moist unit weight, and reminder of the concept that dry unit weight, moist unit weight is larger than that, saturated unit weight is even larger than that. So you have those in the correct order when you're doing a problem. I've got typical G sub S values, typical specific gravity values there. For sand, silts, and clays, so we're talking 265 to 272. Good to have a good reference to those in your mind. Typical values for moist unit weight of soil, 100 to 125 pounds per cubic foot, or 16.1 to 20 kilonewtons per meters cubed. We're looking at SI problems. Most all the problems are going to be in SI. So that's one of the unusual things. Geotech world still very much in the English units, but the exam will have SI problems on it. Moisture content is going to vary between 6 and 20% for most all common soils out there. If you do a calculation, you come up with a 45% moisture content or a 2% moisture content. I'll tell you something's wrong with your answer. Void ratio somewhere between 0.5 and 1. So if you start getting 2s or start getting 0.3s, that tells you you've got something wrong with your answer in there. If saturation changes in a sample, the moisture content changes in that sample. Big concept in soil mechanics, weight of solids. The weight of solids is what we have constant once we work with in soil mechanics. That's what we keep track of. The moisture content can go up and down in the sample, and that'll change the moisture unit weight. But dry unit weight is always constant. So weight of solids is something we want to try to determine and use that for doing all your calculations back and forth. The effective stress equation, there will be, without a doubt, probably an effective stress problem on there. Effective stress equals total stress minus pore water pressure. They're just going to give you a simple situation with the soil profile and ask you to calculate the effective stress at some depth below the ground surface given a certain water elevation. So you know you're going to see something very simpler like that. Don't forget that if you're drawing or looking at calculating effective stress, if you're below the water table, you can go straight to using a buoyant unit weight, saturated unit weight minus unit weight of water. To get you your answers quicker. So there's some problems in here that if you know how to do effective stress calculations using buoyant unit weight, it's done in 15 seconds. Done in 15 seconds. Second sheet, start talking about permeability. Two different equations for calculating flow to a soil media. Q equals KIA. What they're probably going to have something more for you is maybe a flow net. They'll give you the flow net, and you need to figure out what, they'll probably give you the K value as well. You need to figure out what your change in height of water is across the project. Calculate the number of flow channels. Calculate the number of equal potential drops. Plug right straight into the equation, get the Q value. If it's a problem that's given you the width of the structure, like the width of the dam, then we need to add the W term onto the end of it to actually get the total quantity that flows under the dam, not just the quantity per foot that we would calculate with this first equation. So you're going to make sure you keep that W in mind. Number of flow channels, number of equal potential drops. If you count the number of flow lines on a flow net, count the number of lines, minus 1 is the number of flow channels, or you can physically count the flow channels. That's why I like to do it. And if you look at number of drops, you look at the number of equal potential drops you have through the system, and then that minus 1 gives you the number of equal potential drops, equal potential lines, I'm sorry, count the equal potential lines, and then 1 minus that gives you the number of equal potential drops through the system. At any point in the system, at point A, the pore pressure at A divided by the unit weight of water is equal to the initial head at the upstream surface of the project minus the number of drops times the drop in head per equal potential drop. So we can use that to calculate what the pore pressure is at any point in the system. Yes?
Can you go back to the lines? I don't think I ever caught that during class. Like, how is after you count? It's always minus 1, but I never know if
we've got a problem.
Oh.
We've got a problem. We'll get with that. It should cover it. If we've got our simplified ground surface for our project site, and we've got a simplified dam, and very quickly, we'll see how good the flow nets work here. I've got a rock surface we're going to say is impermeable to make the problem simple for ourselves. Go ahead and put everything we need here. Water surface upstream, water surface downstream, and if we could draw our everybody remembers the fun of drawing flow nets, right? Well, not the best looking flow net in the world there, but you guys get the general principle. So we can count equal potential lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 minus 1 is how many drops we have. So I can also count drops. 1, 2. So this is 1 drop. This is the second drop. 3, 4, 5, 6, 7, 8. So I've got 9 potential lines. I've got 8 drops in that system. I've got flow lines, 1, 2, 3, 4 flow lines, so 4 minus 1 would be 3 flow channels, or we can just count 1, triangle, 2, and 3 flow channels.
Now, what does that actually tell you?
If we draw our flow net correctly, which means we have to have all these intersecting lines all at right angles to each other, every point in the system. If we have our squares drawn in here like we should, so we can put circles inside our squares. We have repeatability of our geometry out at the end on each side. If we get that all together and working properly, these are perpendicular lines. we get that all together, then that helps us solve the equation for the flow underneath the structure. So we can take the number of flow channels, the number of drops, the change in head, the big delta H, which is right here. We know the K, we're going to be given a K for the soil. And with that, we can calculate the quantity of seepage that's going to flow underneath the structure and daylight downstream of the structure. But we've got to draw it to scale, and we have to draw it and follow all our rules that we've got for flow nets. They're not going to make you draw flow net. There's no way they can put that on a little fill on a bubble sheet, right? So they're going to give you a flow net and maybe have you pull this information off of it.
In one of these practice exams, it's exactly, it looks like that. They have it drawn right here, and they ask for the flow rate per linear meter.
Okay. So they're looking for Q equals K delta H, number of flow or number of drops, and that's going to be, if you got meters in this, that's going to give you the flow per meter into the board. That's what that'll give you. And if they tell you it's 100 feet long, then you got to multiply it, or 100 meters long, and you got to multiply by that with W to get total quantity. Okay?
Is H type the water on this side?
Delta H.
No, I mean H only. H.
If you're looking for just H, it's in reference to your datum, wherever your datum is. If that's your datum and you keep that datum for the whole problem, that is your H. You could use the rock surface if you wanted to. You can use any point you want. You just have to be consistent through the whole problem. Consistent through the whole problem. All right. So since we've got a flow net up here, if I had this point right here as point A, I can find my H value. I can count the number of drops. 1, 2, 3, 4, 5, 6. So I've got 6 drops. So N sub D is going to be 6. My little delta H, little delta H is big delta H over the number of drops. So this is the drop. This delta H is the change just across one equipotential drop. So these are all little delta H's in here. So if I want to find the pressure at this point, I know what this pressure is, and I can take away 7 increments of delta H, and it gives me the pressure at point A. Shear strength. More Coulomb failure criteria. Shear stress on the failure plane of failure is the cohesion plus sigma n tan phi of the soil. They're probably not going to give you anything that's got cohesion in it, quite honestly. So you're just going to end up with shear stress on the failure plane of failure without that term in there, the sigma n tan phi. And they may give you phi, and sigma n asks for tau. They may say, here's tau and sigma n, calculate phi, something of that nature. I don't think you're going to see anything on confined compressive strength, so I'm going to jump across that pretty quick. I haven't seen anything since I put that in there. Earth pressures, you know you're going to see earth pressures on the problem, on the exam, without a doubt. And if you look in the book, what they refer to in the reference manual is Rankine's earth pressure theory. It's kind of one of those things you probably want to memorize. Case of A, that's the active earth pressure. That's when the wall moves away from the soil. When the wall moves away from the soil. Case of A is tan squared, 45 minus phi over 2. That value should be somewhere 0.33 to 0.5 as its range, so that the wall is moving away from the soil. You've got the condition where the wall is moving into the soil. The wall is moving into the soil. It's the passive condition, case of P. Tan squared 45 plus phi over 2. One way to remember that is case of P, E for plus. So you have plus in the equation. Helps you remember, get those equations going correct. I did an exam when I was an undergrad. I got this backwards, and it cost me dearly on that exam. So you'll try to remember that. Case of P values are 2.5 to 4. A lot of times you'll see 3s, a lot of 3s for case of P values. And I've got some examples there. And it's all function of friction angle. So if you've got a friction angle of 30 degrees, your case of P is 3. If you've got a friction angle of 30 degrees up here, you end up with 0.33. exactly opposite of each other. And in the third condition, if we have no wall movement, top of the wall can't move, basement conditions, things of that nature, then we're going to have our at-rest earth pressure condition, K naught, and that's 1 minus sine phi, and for a 30-degree friction angle, that's about 0.5. So here, those are all functional friction angles of the soil themselves. And here's our classic earth pressure diagram. We've got our increasing pressure. This is a single soil condition. We've got our increase in lateral pressure as we go deeper in the ground. At any one point in this system, you could write the equation, but if we write it for at the bottom, right here, sigma h is K sub A, h, which is the height of the wall, or height in the ground you are, times the unit weight of the soil. So we could calculate it at any one point, just if this is our depth h, and calculate what the pressure is at that depth. So that's a pressure. That's a pressure. P is a force. P is the net of all pressure on the back of this wall. 1/2 gamma m h squared K sub A. That K sub A value, or that K value could be K sub A if we have the active condition, K naught if we're at rest, or K sub P if we're in a passive condition. You're typically going to see a K sub A on the exam, I almost guarantee you. You might see K naught, you're not going to see K sub P in this kind of situation. You're not going to see that. So, if you have a problem that does include water behind the wall, remember that K for water is 1. K for water is 1. And of course, that's why we don't want water behind our walls, because that's what tends to push them over, is that high hydrostatic pressure on the back. But, yes?
I don't see it in here, but just make sure, they won't give us a slope back base, will they?
No, they're not going to be anything complicated like that.
Okay. That's the
They're going to give you walls with vertical back faces and horizontal ground surfaces. That's the kind of stuff they're going to give you. And here again, you look in the reference manual, that's the references they're going to give you, so you have to memorize it if they didn't have it in the book. They're not going to do that to you. They're not going to do that to you. Settlement. Settlement compressibility of soils is the other major area we might see. We've got our E log P curve, void ratio on the y-axis, pressure or stress on the x-axis, and that's the result of a test. We run a consolidation test in the lab. We produce that consolidation curve, and that tells us how the material is going to change in volume as we put additional load on it at the ground surface. Important things to know, we've got C sub C value, coefficient of compression. That's the change in void ratio over the change in pressure, and all we're looking at is the slope of that line. That's all we're looking at. This x-axis is typically plotted in log scale. E1 minus E2, log P1 minus log P2 minus log P1. That'll give you the slope of that curve C sub C. C sub C and C sub R are related to each other. C sub R is a recompression curve. Those vary by ratio of about 6 to 1, 10 to 1. I don't think you're going to see anything on C sub R on the exam, actually. If you see anything, it's going to be on C sub C value. Rule of thumb, I have seen this on problem on some examples I've seen. Rule of thumb for C sub C, it's approximately equal to 0.009 times the liquid limit minus 10. Some folks might put 0.007 in front of that instead of 0.009. But that is something that could very quickly ask you they can give you all kinds of properties, but never really give you E log P curve, give you the liquid limit of the soil, and then you can still come up with C sub C value for doing the calculations.
Do they base off of that, or is that just, 0.007 is going to be different?
Well, that's an argument between professionals on which value it should really be. So 0.009 is a very common value to see people actually use. If we look at compressibility of soil, we're talking about change in the vertical direction. So if we look at change in the void ratio over 1 plus E naught, that initial void ratio of the sample, we can plug it in to get the settlement of a layer. Where the settlement is H sub S is the thickness of the layer. You know how we did some things where we talked about time rate of consolidation, and we talked about how the water particle would travel out of the soil. And if we're doing the overall calculation, we want to know how thick the soil is, but we want to figure out how fast it's going to consolidate. We look at how far the particle of water has to travel. So it could be HS over 2 in the time rate problem we'll look at. That's what I'm talking about right here, HDR for the drainage. The drainage path could be single or double drainage. We have a soil layer, ground surface, and let's say we've got a few different layers down here. In a particular case, if we had rock down here, that we would assume that it's impermeable, and we have a clay layer here, and we have a sand layer on top of that. If we were looking at drainage lengths or HDR, that's how long the longest path is for the water particle to get out of the sample. If this is an impermeable surface, water can't go down, so that the farthest traveled distance in this particular case, HDR is going to be the full thickness of that clay layer. If I would remove this and find that we have a sand layer down here on the bottom, so that the water can drain out the bottom of the clay layer, both the top and the bottom, then the maximum distance a particle of water would have to travel would either be that direction or that direction from the center. So in that particular case, we would have double drainage, referred to as double drainage, drains the top and bottom. This is single drainage, it drains only one direction. So that's what H sub dr is. C sub V, coefficient of consolidation, that's used in our settlement, our time rate. You know, with respect to settlement, we talk about how much settlement we're going to get, and then how fast it's going to occur. So to help us with how fast it's going to occur, we want to use C sub V. It's not C sub C, it's not C sub R, it's not related to those values. These are used to calculate the quantity of settlement. C sub V is to calculate how fast it's going to occur. And we use our time factor equation for calculating that length of time. C sub V is the property of the soil. Typically probably going to be given to you on any kind of exam like we're talking about here. T sub C, that's the time it's going to take for the consolidation to occur. HDR is the drainage path length, we talked about up here. Our time factors come off page 141. They are in the book, so this is a valid problem they could give you. They'll give you the time factor, or ask you for a certain period of time. You calculate the time factor, and then you can see how long it'll take for that to actually occur. And we've got problems like this we'll go through here when we get on the board. Influence charts. They do have influence charts in the book. We're talking about the change in stress or the loss in stress versus depth below some kind of surface loading. If I build me a tank up here, it's 30 feet high, 200 feet wide, it's going to put a stress regime into the soil below it. Now, the further we get from the tank, the smaller that stress increase is going to be, and the further we get horizontal, the less the stress is going to be. So we use the influence charts we have for either a circular tank or a rectangular area and calculate the stress at any one point below that surface loading. Blizzardesque is the most common methodology to use for this. Westergaard solutions also exist, but it only really applies to very specific, unusual conditions in the soil mechanics world. So we'll be looking at the Blizzardesque solution for that problem. And like I say, it's all in charts, and we'll go through those as example problems. Shallow foundations, for those who had foundations, we're missing a whole bunch of terms, aren't we? We're missing a whole bunch of terms. That's the basic, simple bearing capacity equation. Can't get much simpler. We've got the ultimate capacity of the soil, cohesion, N sub C, unit weight of the soil, depth of the footing, N sub Q, 1/2 times the unit weight of the soil that's below the bearing elevation, footing width B, and then gamma. C, Phi, and the unit weights, those are all soil properties for the soil, and that's going to be given to you in this kind of a problem. Bearing capacity factors, they're all a function of the friction angle of the soil that you're looking at. Good rule of thumb for a factor safe for shallow foundations is 3. And in utilizing that, if you want to get the allowable pressure you can put on the soil, it's the ultimate pressure divided by factor of safety. And here, if you put a 3 in there, that it gives you less conservative value for your results. Mentioned that they use different symbology in the supplied reference. Here's a short, quick list of them. We'll go through the paperwork and show the sheets out of those supplied reference window. I'll actually apply these into it to help you out. WT and W, they're synonymous. VT and V for total volume of the sample. Gamma, if you see just a gamma, assume it's gamma M, gamma moist, or gamma T for gamma total. Total meaning it includes both the water and the solids. Gamma M includes water and solids. So if you just see a gamma, assume it's gamma M, and you'll be okay. Gamma prime equal to gamma buoyant, gamma B. Here again, that's if you're below the water table and you're looking at effective stress issues. I like the prime symbol myself, but gamma B is out there as well. They use P naught for sigma naught, so that initial overburden pressure at any one point. They use P sub C for pre-consolidation pressure. We use sigma P. They use delta P for change in stress. We use delta sigma. They'll use Q sub S where we use little q. So those are all things that, like I say, they're on the sheets I've given you to keep in mind. So when you get in there, you're not looking for sigma values, because you're not going to find them. You're not going to find them. There's going to be P values there. A couple other sheets that I've thrown in to help remind folks. I have seen some classifications, type of problems where you have to find your D values. If you want to find your D60, you find 60% passing on this side, D. Come over to intersect your gradation curve, come down and get the diameter, and that is D, referred to as effective diameter D60. Can't be too far over there. And remember, this is log scale. This is log scale across the bottom when you're pulling those numbers off there. So you can find your different D values. That should actually be D30 right there, not D60, D30. The cut and paste got the best of me there. So these are actually the effective diameters for D30, D60, D10. Those are commonly used in classification of soils. We also do pull D15 and D85 if we're dealing with filter design. Yes, ma'am.
Did you say it was 30, 60, 10, or 60, 30?
It's 60, 30.
Okay.
60, 30. Yeah.
And that's 64 to 60, correct? Up above.
You what now?
The 64%.
64% in this particular sample.
Oh.
64% is passing the number 4 sieve, and 10% passing the number 200 sieve. And here again, those I've called off because those are delineations between fine particles and gravel. So sand is in that intermediate range there. So that came off of some problem in one of the class assignments is where it came from. Remember the Unified Soil Classification System? That is a sheet that's in the book, although I've never seen a real good example problem anywhere that references it, but they do provide you with the classification chart to classify materials according to the Unified Soil Classification System. Biggest thing is to remember our divisions and where our breakpoints are at. Number 4s or number 10s or number 200s for our sieves to make sure you're calling a sand in this particular system. There is the ASHTO system out there. They do provide that as well. It's a different set of breakpoints. They don't have fine gravel. They don't have medium sands. So you need to try to keep track of where these breakpoints are as well. So if you're classifying something by ASHTO, it uses the correct size particles. Yes, ma'am.
Is it is it greater than, or like, they say, what is a 75 millimeter diameter, what is it? So is it,
That's the break point between a cobble and a gravel.
I mean, how would you classify it though? Is it greater than 75 or less than 75?
If it's retained on it, then it's the same.
75.
If it's retained, yeah, if you had something that's retained on the number 3-inch sieve, then that would be a cobble sized particle. If they say everything past the number 3-inch sieve and was retained on the number 10 sieve, then that tells you everything was retained in this size and you would have gravel. I'd rather look at that one, because that's unified is the most common
So
system.
the question was, if you have a 3-inch stone, is it a boulder, a cobble, a gravel, sand, or silver clay? Via cobbles.
To call out a specific size is an unusual way of talking about it, I guess I'd say. You know what I mean? Typically, they're going to give you a gradation curve, and they're going to say, they're going to give you a gradation curve, and they're going to say, what's the percentage sand in that sample? And you need to realize that you need to go from the number 4 to the number 200. Number 4 had 10% passing, and number 4 had 64, so there's 54% sand in that particular sample.
So we need to remember these breakpoints.
I would. They're on that chart as well. But it's
What chart?
it's in the.
Pages 137 and 138 in this other handout. Thank you, Jessica. You're welcome.
She's on top of it. She's on
Have
top of
sleep.
it. So that is in there. So it's kind of one of those things. There's a simple things you just keep in your mind, and then you can move quick. You know, you're always looking at those half a dozen or 2 dozen or so problems that you can just peg real quick. Take those seconds and minutes and use them somewhere else, maybe where you're struggling a little bit. Any other questions on gradation?
Yeah, I mean, like, what you're saying is we do not have to memorize that cobble is between 33 millimeters.
No,
'Cause
it's
here.
there. But if
But-
you have a good idea going into it, it's better than having to seek it out on the table. So there's a lot of information on that table they've got.
Can you tell us where that's at? I don't see, I mean,
It's here on the next
I don't know
page.
cobbles, but I know the main ones, but, you know, if they ask me about cobbles, I'm not gonna have that one.
Well, they're not going to ask you. They're not going to ask you.
So
about
down at the bottom says stone fragments, gravel, sand. Makes it an A1 because it passes.
Where are you, Jessica, are you on page 138?
I'm on the top of 138, yeah. If you had less than 30% passing of 425 millimeters, then it would be stone fragments and sand. There.
Oh, I see it now.
Yeah, it's at the bottom, right?
It's just not, it's not as
It's
easy
at
as
the bottom.
written.
Right,
Yeah.
it's not that simple.
This is a whole lot easier in my mind.
Yeah.
Whole lot easier in my mind.
Do you have
But I
one
won't
here?
remember.
There's A1, A3, A4, A5, A6.
And then while we're here, before I forget it, one of the things you need to remember when you're doing an ASHTO classification, I don't have the chart up here to be able to show you, but you can see the chart on page 138 in the second handout that I've given you. When you're doing and solving this classification, you always start at the upper left-hand side and work to your right. And keep working to your right and checking conditions until you find the first sample name that works. You go until you find the first sample name that works, and then you stop, and that is it. If you keep going to the left, you'll find another one that works. And you keep going to the left, you might find another one that works. Or if you come back from the right, you're going to be all messed up. So you always want to start on the left and solve as you move to the right, and stop at the first one that it does meet that criteria.
So they could potentially ask for the group classification, and we would have to give them the A-2-7 or something like that.
Correct. So that, and I haven't seen an ASHTO example problem anywhere, so I don't know if they'll actually ever get it or not, but it's in the book.
A-7, 5, and 6, they're the same thing.
There's an asterisk there in the bottom of the chart. It's based on the
I see the asterisk underneath, but I don't see the asterisk in the chart. I see plasticity index, but not for 8-7, that's why. I think I remember that for 5, so it was.
for the A-7-5, the subgroup is equal to or less than liquid limit minus 30. You're in A-7-6. if the liquid limit minus 30 is, if it's
Greater.
greater than the liquid limit minus 30. Yeah, I'm not sure I see their asterisks on there very well either. I just point that out.
There is one for plasticity index, just not on the, group.
Right below the
But I understand why they have it there.
Correct.
Yeah.
Correct.
Makes sense.
So that's everything in the 9 pages I said you might want to know. So now we can look at the second handout I gave you. This has civil engineering at the top. Starts off on page 134. You flip in the book to the civil engineering section. Of course, the most important thing they talk about first is geotechnical engineering. It is the one part of the test that has 15% of the exam. There's no other part of the exam that has 15%. The next closest is 12. So geotech is definitely the most important subject on the exam. All joking aside, this is actually what you have to work with. These pages right here, they're out of the manual, out of the slide reference manual. These are the pages you've got to work with. So if you come familiar with them here, you can find them in the book, hopefully in a timely fashion. Don't want to go through these things in detail. Here again, it's kind of difficult to see what's on the board up here. But what I've done for you guys is went in and put gamma B or WC, or reminded you that V sub S is not soil, it's volume of solids, and gamma M, and the V sub T's, VWs, or VTs and WTs, to remind you of those kind of things that you're not going to see those when you get to the exam, but remember where they actually are so you don't get lost. I've got some extra indicators up there of equal potential lines. This is an equal potential line right here. Ground surface is an equal potential line, both upstream and downstream. They call them out inside here, obviously, as equal potential lines, but that top and bottom is an equal potential line. I call the flow channels out here again, all the way across the bottom flow channel. A flow line, and there's a flow line all the way across the impermeable layer at the bottom. So be aware of where those are at.
How do we, I'm sorry,
Okay.
how do we analyze if they have that, I don't know what that is underneath there. Yeah, let's take a key, but how do we,
That's an impermeable boundary that they put in to slow seepage down.
right, but how, I understand that, but how do we analyze, like, counting through and into the equation? Is it still just the same process?
Still the same. So if you're going to count drops, there's 1 drop, 2 drops, 3 drops, 4 drops, 5 drops, 6 drops, 7, 8, 9, 10, 11 drops.
Wait, 12.
There's 12 lines, there's 11 drops.
There's 12 drops.
I think your laser is jumped over.
Yeah.
That, you got
1,
five
2,
there.
3, 4, 5, 6, 7.
I think it's 11.
No, there's 11. That's not a flow line right there.
Yeah, that's 11.
That's an arrow. It's an arrow. So there is only 11. I can count. That's proof I can count.
That's mean.
That is.
That is somewhat misleading there. It is somewhat misleading, but not sure what you can do about it. Not sure what you can do about it.
Well, it's not a question of the test. It's just-
Next sheet.
Oh.
Here again, all I've done is gone down through here where they used PC. I put sigma P, capacity consolidation pressure, sigma naught for P naught, delta sigma for delta P. So you've got those terms refreshed in your mind. So when you go to find them on here, they won't look much different. Sigma 1, sigma 3, tau max. Instead of just the symbol T. I've never seen a Morse Coulomb actual problem on the exam from a soil mechanics side of the brain. Now, you might see it over in materials. I added a little bit of additional notes on here. This is vertical pressure, horizontal pressure. So this is just the vertical forces behind the wall. You multiply it by your K value, K sub A, K naught, KP, whatever that might be, to get your horizontal values. And like I said, I really anticipate you're gonna see a case of A kind of condition on what you're doing. I have seen some examples, some problems where you just have a simple sliding block. Simple sliding block where you know the weight, you know the angle of the slope, and they ask you to calculate the factor of safety with percent of sliding for the setup they've given you. So real straightforward vacuum mechanics type work. Facing the wrong way, but that is everything you need to know about classified soils according to the Unified Soil Classification System. When we did it in class, we had those charts that you had the branches that kept branching to the right. I like that system better than I do this one personally. But they could maybe give you some different properties of material, and you have to run through and figure out what the group symbol is in this column right here.
You still just go left to right, right?
Yeah, you want left to right on this one. Left to right on this one.
Left to right, correct?
Yes.
Left to right, right?
Yes. Plasticity chart. Do they have you plot a plasticity chart values on there? Here's your C sub U and C sub C for calculating the if a material is well graded or poorly graded on a gradation curve. That's what all this in this area up in here is for. Here again, this is giving you the well or poor graded portion of some of this material down here. If you have the GP or the GM or the SP, SW type materials.
Plasticity chart, wasn't there another line on there?
This does not show the U line.
U line.
The U line, and that's correct. That's just a safety to make sure your data looks good. Plasticity chart.
That's just the upper
We
down.
have our little. This is the A line after Mr. Atterberg, and there's another line up here called the U line. Nothing can plot up here. Nothing can plot up here, and of course, you know that's at liquid limit equals 50.
Wasn't there like an M too? That was straight
Um,
across?
Say it again.
Isn't there like an M that was straight across or something? Yeah, right down there.
Well, this region right in here will be the MLs.
Oh, that's.
This region up in here is the CLs, the CHs, and the MHs. And this little zone here was the CL ML material.
Yeah, that's what it was.
Organics like they're out there too.
The organics could plot on here, but everything's going to be inorganic. And those are on here. That's actually a CL right there. There's an ML, it's MH, and there's a little CH right there. So that's all on that chart.
No, see it like.
And this is Plasticity Index over here.
You think they'll ask us who the godfather of geotechnical engineering is?
I hope they do, because if you guys missed that one.
Teriyaki. Is that
Between all the exams
what
you've taken from me, you probably got, what, 7 or 8 points total out of that?
If you had put teriyaki on that test, I would have got it wrong. Because I would have done it like autopilot.
On the one I've currently got right now, by the time it gets to the Soul Mechanics final, there's 16 different names that begin with T and end with I.
You have to put teriyaki in there.
I need to put that on there.
That's how I remembered it, because it's almost like teriyaki.
Yeah, I need to do that. I tried to toughen that up to set it up, memorize the T and an I.
16
names.
names.
Trying to trick people. Start calling you Corman.
Maybe I should start putting
Thank you.
Carl from everything. Maybe I should do
Where's
that.
your PhD in instant recall?
I didn't mean the good. I didn't mean the good sense.
Here's the ASHTO chart we're talking about. Like it says right here, stop at the first classification that works. When you move from the left to the right, stop at the first one that works. The way this chart's set up, the material to the far left is the best material that a highway project would like to see. Very coarse grained, very strong, very free graining material. As you move to the right, the material gets worse and worse and worse. In the ASHTO or the transportation world, you do not like A75, A76 soils. There's the soils you dig out and replace. And like I say, it tells you how things are grading here, whether it's acceptable or not. Got group index, real simple calculation, just a function of the plasticity index defines the liquid limit. GI is another indicator of how well the material is suited for a transportation type project. This whole system is set up around the transportation system. A GI cannot be negative. You calculate a GI and it is negative, the value is 0. the value is 0. The smaller the value, the better the material is. So if you got something that's an A76 with a GI of 35, that's just horrible, horrible stuff. Horrible stuff. Bearing capacity factors, we talked about that. My little 9-page things you might want to know. Based on the friction angle, this is really one chart, if you will. They just kind of blown it up so you can use it a little more effectively. You've got your 3 bearing capacity factors in both of them, depending on your friction angle or your soil. Come up, get your bearing capacity factors, throw it into your equation, and get your ultimate bearing capacity out of it. This is the stress distribution underneath an area. It's a very practical application, but we have a point load. If we have a point load, we can determine what the stress is in the ground, distance Z in the ground, distance little r from that point, or x and y from that point, and find out what the vertical stress increase is at that point. Get your r, x, and y values, z values, dump into the table. Get your factor, multiply that factor times the peak value, and that gives you what that force would be. More likely, you're going to see a problem come off of the stresses below a tank chart. And with this particular chart, you remember big R is the diameter of the radius of the tank. Little r is the distance from the center. And this gives you the influence factor, I. We refer to it as IZ in our class. For the stress at any point beneath that tank. So if you know your value of big R, you know your value of little r, and it could be you want it at the edge of the tank, so big R equals little r. Get your ratios, come into the chart, and pull out your influence factor. Your influence factor times the surcharge the tank puts on the ground gives you the stress increase, that delta sigma z, that stress increase we're going to have at that particular location. If it's directly beneath the tank, at depth z, or if it's at the edge of the tank. Now this is a simplified chart. It's only at the center and at the edge. They can't ask you at any other place around the tank because the chart doesn't give it to you. We use tables when we did it in our class, so we can find it at any point underneath of it, outside the edge of the tank or anything. Yes, sir.
So that R was E gives you the I. How does that I relate to the CR value? Is it?
There's 2 separate problems, if you will. 2 separate problems. For some reason, they want to call that one in that table up there C.
Yeah.
In my world, they're all I values, influence factors. They're all IZs, if you ask me.
That's how it is in
So
our textbook.
all of those are IZs?
Yeah. In the textbook we referenced, they had I1, I2, I3, I4. Just made it confusing, if you ask me. You just got to know which one you're looking at, which chart you're looking at. And the IZ value times the surcharge load, piece of S from the tank, gives you the change. And here they call it IP, or delta P. We would call that delta sigma Z.
How do they get a CR?
I have no idea.
That's a good answer.
I have no idea. I wish I could change the values and the symbology they use in this book
Glad we don't have to.
so much, but I'm not quite there the capability to be able to do that.
Have you ever seen these problems in the test, really, or do you think that's clear?
I don't know that I've seen a problem like this, quite honestly. I don't know that I have. The other influence chart we have is for a rectangular loaded area. So this is calculating the stress. I've got a loaded area that has some Q value on it, and I've got some value Z in the ground beneath this corner. This chart setup works around the fact that we calculate the stress at the corner of a loaded area. So we go in, we know what our length is, we know what our width is, we know what Z is, and we can come into the chart. The M value, so we call this B, and then also we've got M is B over Z. N is L over Z. We calculate those two values. We come into the chart, find the N value. Whichever one it is, says N point is equal to 0.25. So that's the curve we're on. We go up the left-hand side, and we go across the bottom side for M, and say the factor was 1. So we know 0.25, 1, this come together right here. We go horizontally across. Our influence factor is somewhere in the neighborhood of 0.068. 0.068 times Q times Q is the change in stress. Just got to move the decimal point over. How about that? That gives us a change in stress at beneath the corner at depth Z in the ground. And what you got to remember is if somebody says, give me the stress below that point. If they want to know the stress below that point, you can only use this chart to calculate stresses at a corner. So what you have to do, remember that? Yeah. Take that area, calculate the stress at depth Z, and then multiply by 2 because there's 2 of them. Right? Or if you had to find it in the center, then you have to do it one time and multiply times 4. Superposition, you can add and subtract them. Add and subtract them. So, and it can get much more complicated, but it's going to be something simple. What they're going to give you, they're not going to give you just a rectangle and one at the corner, because anybody can go in the chart and do that. They're going to give you, they're going to want it at the center, or they're going to want to know at the midpoint on one side. So that you at least have to find a value multiplied by times 2. That's what they're going to do. They're not going to get anything more complicated than that. But make sure you know how to use that chart, because it is a little confusing. It is a little confusing. Top chart deals with consolidation and floor pressure changes. We did not go over anything of that in our program at all. So if you see a problem that requires you to use that,
Yes.
sorry about your luck. Sorry about your luck. We did use this chart at the bottom. We used it in tabular form. This is the time factor constant, T sub B. And we had the T sub B values, time constants, for different percentages of consolidation. Remember I told you a couple of them you should remember, if you remember what those were? One of them was 50%, right? 50%, 0.196, and 90%, 0.848. Those are the 2 common increments of time that we usually care about and do our math around when we're doing any kind of design calculations or settlement analysis. The graph they show there is the same data. It's the same data, just shown in a different format. So if they wanted to know what the consolidation, the time to 50% consolidation, we come into here, 50%, get our time factor, put that into our equation that has C sub B, T, and our drainage length on it, and we can calculate how long it took for consolidation to occur to a 50% value. So that's the quick review on what I think you'll see on there, the pages out of the book that I think that I know you'll be using for the soil mechanics world. You guys want to take a break, or do you guys want to keep going before we can't crank on some problems? Take a break. Can somebody kill the camera, please? Are we on?
Yeah.
All right. I've got some problems here that we'll run through. And when this is over with, I've actually got clean sets of these we can get to you. You guys can cruise through them again if you want to practice, although it is getting close to the exam. So, got a sample we took out of the ground. I'll read the actual exact problem, I guess. A cylindrical sample, 50 millimeters in diameter, 200 millimeters long, was extracted from the ground and coated with paraffin wax to prevent loss of moisture. The wet weight of soil and wax is 7.9 So I guess this is soil and wax. 7.9 newtons. The weight of the wax is 0.5 newtons. Dry weight of the soil, salt of the soil is 6.54 newtons. Unit weight of water, 9.81. Specific gravity is given as 2.7. And they would like to know what the moisture content, water content, the bulk unit weight, the dry unit weight, the void ratio, the degree of saturation, and the effective unit weight, or the buoyant unit weight, is of the sample. So, moisture content, how do we get moisture content?
The weight of the water over the weight of the solids times
Easy
100.
W minus W.
Weight of water over the weight of solids. Remember, we do everything with respect to solids. So how do we get the weight of solids? Given. How do we get the weight of water?
Total weight
So
minus
we
wax.
got to subtract these two, right? So we can go to 7.9 minus the 0.05 minus the weight of solids. 6.54 over the 6.54, and that gives you 20%. Just so happens to be answer B on the example problem I got. How about the bulk unit weight?
That's given W.
W over V.
W over B. Total weight, because this includes M, it's going to include both the solids and moisture. So M, or W is going to include the moist condition, because that's how we took it out of the ground.
I'm gonna have the specific gravity solids.
So, and 7.85 divided by the 0.393 meters cubed. That's the volume. You're given the diameter, you're given the length. I surely don't need to calculate volume for you at this stage of the game.
Well, every time
problems.
Whenever I see that D and L, I just think of dead mild blood pressure.
There you go. Gamma D. It's real simple. Don't overthink it. You got the wet weight.
Should we refer to the previous one?
You got the wet weight. So you got gamma M.
Yes.
1 plus moisture content.
I'm trying to figure out.
Did
All you
you
need
get
to
the
do is-
water out for
What's
the
that?
previous,
What is the equation for the top part of that?
the second
The
one?
second.
This part here,
Down,
Bottom?
down, middle one.
Yes.
Yep, W.
that's W over V.
Where's 7.85 coming from?
7.85 is actually the difference between these two.
I thought
Sorry.
we were using the total weight.
This is soil and wax minus wax.
wax.
Remember we
I
waxed it
couldn't
when we
even
run?
read what you had up there. Why is it
Why
wax?
is there wax in there?
Yeah, somebody gets the wax.
Because in the real world, you would wax the sample and bring it in. That's the one way of preserving a sample so the moisture content doesn't change. Is to actually melt wax and coat it with
Or
wax.
you put it in a jar, right?
Well,
No.
you can put it in the jar, but you gotta have one big old jar if you're taking a, a lot of times you're gonna go out and take a 1 foot by 1 foot by 1 foot cube of soil out of the ground.
So what, you
You
melt the
cover
wax
wax?
out?
Melt the
And then
wax,
you get the
and then
flake
just
of
cut the
wax.
wax off.
You cover the whole thing in wax.
But wait, when you cut the wax, when you peel the wax back, isn't that gonna have like all this soil in it?
No.
Just a little bit.
I don't believe that.
It's special wax.
And
Dirt wax.
so, dry unit weight.
That makes sense.
Don't overthink it, it's just the moisture unit weight divided by the 1 plus the moisture content, to take the moisture content issue back out. So it's 7.85 over 1 plus the moisture content. Oh, what's the moisture content? Moisture content was 20%.
Correct.
Is that on our equation sheet?
What's that now?
Yeah.
These are some of the things you gotta have memorized.
No, it's on.
Sorry.
Oh, it is on there?
Yeah, or you could have done the weight of solids divided by volume.
Isn't that 20 on the numerator? 20 kilograms per meter?
Where?
Your gamma M is 20.
20%.
You put 7.85.
Oh, yeah, I did. Sorry. Sorry. Good eye, good eye. And of course, our dry unit weight's lower than our moist unit weight, so that makes good sense for us. Dry unit weight's gonna be less than moist unit weight. What was the next one? E. E. How you gonna calculate E?
Volume of voids over volume of soils.
Okay.
I like how the soils team is answering all these
I know
questions.
N equals E or 1 plus E.
It must be
Well, if we had a bridge review session, I'm sure.
How you gonna volume of voids over volume of solids?
It's the gamma of the moist.
The way I solved it was going and saying that I know the dry unit weight, G sub S, gamma W,
1 plus E.
over 1 plus E. That's one of those on that, remember that little short list at the very top said memorize? Memorize? That's one of them. You know gamma W, or you know gamma D, you know G sub S is given, you know way the water's always known, the only thing you don't know is the E.
This one's actually in the FE too, or the manual.
That equation?
Yeah.
So,
Gamma D, second
Yeah.
part, gives you 2 equations.
so and if you do all your math, 0.586 is the value of E, which makes sense, 0.5 to 1, something like that. Saturation, how are we gonna get saturation?
FC equals WC, GS.
Yes,
I
exactly.
knew that one.
SC is G sub S, WC. You know E from here, G sub S is 2.7, moisture content is 20%. Come up with a saturation of 92.2%.
Is that equation given somewhere?
This one?
Memorize.
I don't know.
I don't know that it is, but that's one of those you just memorize for life. I mean, that comes in so handy, you just, I mean, if you're doing these problems, it comes in so handy in so many ways. Not even funny. Now, personally, if I'd done this problem and came up with 92.2, I would have said, ooh, that sounds awful high. That would have been my first gut reaction when I solved this problem. Seems kind of high, but that is the answer. That is the answer. So, in nature, you don't see 92% moisture content, or saturations out there. In nature, you don't see that. Now, I can force it in the lab, but you typically don't see that in the field. Even in the flood prone area. No. No. And buoyant unit weight,
Chemostat minus gamma W.
There's several equations for gamma sat, G sub S plus E, gamma W over 1 plus E.
so you just need to grab an equation, calculate the saturated unit weight. You know, this is 9.81. And for this particular problem, I didn't even solve it. I just got to do it to that extent. Calculate what your buoyant unit weight is.
Wait, how many gamma set?
What's that?
How much of gamma set?
There's
There's
several equations.
multiple equations in your reference book.
Oh.
Multiple
Now-
equations in reference book.
It may have been you have asked this already, or another at our review session. Do they give us problems like this where this problem depends on the answer to your problem? Surely not.
This makes sense.
Because if so, then if you mess that first one up,
No, because
all 6 of them.
They
are
can't do that.
Well,
That'd be
I don't think
cool.
they do that because I think they have a random sample of problems they choose from. So,
I mean, these are example problems I've seen. Not, because you can many times get to an answer without going back through and using the previous answer.
yeah, they'll always
Like
They'll
if,
give you
if
an
number
answer
2
to
is
that.
this, then what is?
Yeah, like if the previous problem is this answer, then.
See, I was
what's
hoping for that, but I can see them doing whatever
So
they
gamma
want.
sat
Maybe they don't know.
is
this?
the
What?
weight of the solids over the volume of the solids?
No.
What's that?
Saturation.
WS.
Say it again.
What is WS over VS?
W sub S
Oh,
over.
wait, that's weight of
weight of
solid
solids.
soil.
Yeah, it's weight of solids, W sub S, yeah.
Okay.
Yeah, that's the weight of solids, it's not saturated in weight.
It's gamma times GS plus E over 1 plus. Then subtract
I have a question.
it's cute.
Okay?
So your weight of solids, or your volume of solid, all that is not soil, so why is that not just the wax?
Do what now? Weight of solids is just the dry weight after I put it in the oven.
So it is your soil.
Yeah.
Correct.
So why does this all say not soil?
Might
It
imply
says-
moisture content.
Weight of solids, not soil.
You want to be careful.
Soil is like in water, typically, it's like in a natural state.
Correct.
So why does it say not water?
Soil includes the air, water, and the
Well,
solids
doesn't
in
weigh
it.
anything.
No, but when you
Water
factor
does.
volume,
Yeah.
when you factor
Volume
volume, it
and
doesn't
things like
count.
that in there, right?
And then your unit weights will be off. If you do just the solids, that's different.
Some people I've seen in class that will say W sub S is the total weight of sample. They think W sub S is W,
Okay.
and it's not. This includes water and weight of solids. The W is weight of water plus weight of solids.
So if it's weight of solids, why does that not include that wax?
Because you're talking about the aggregate solids,
Yeah.
not some extra thing that
Not the
was
mixture
thrown
that
on
you
there.
have.
The wax is just.
I mean, that'd be like
something to
taking-
bring- You're not ever gonna
everything
analyze that
in.
wax. That's just something to trick you to throw
But
it
why
out.
do they put that in there?
To
Hey,
make
just to
you
be
know to pull
cruel.
it out.
Just to be cruel.
Just so at
Plausible
the exam
distractors,
time, I can
is
say,
what it
wax? I've never seen wax in a soil problem before, and freak out.
I think it's the way you have just not soil is really.
Here's a question
I'd
that
like
should
that
take
weighted out on
you,
my exam.
that should take you all of 6 seconds to do on the exam.
Okay.
The liquid limit is determined in the Casa Grande cup method, is obtained when the number of blows is
25.
20.
26, 20, 25, or 10. 25. 25.
Yes.
That's one of those ones you just ought to
That
just,
like scared me, like,
you ought to just, that one you ought to hit and be done, and you've got 2 or 3 minutes to put on to another problem.
I mean, I can't tell what you're feeding me.
did you not know?
Probably gets like 20. Probably gets like 10 for assumption.
Let's see here. Next
I
one.
didn't know, but I know 25 will count that for very special.
I was thinking of tamping. That's 25 too, and I was like, I can't have to do the same.
I say, I also remember this.
It's like if 2 answers are both C, one of them's gonna be wrong.
One of them's wrong.
One of them has to be
Can
wrong.
you imagine if they made all of the FEs C?
That's your
Oh
main
my
goal.
gosh.
You-
I would
you have
freak
to
out.
break down the main goal.
Or can you have like your answer sheet if it made the picture? And you write
Soil.
the end of it? Oh my
A
gosh.
soil has a liquid limit of 80, a plastic limit of 40, strictures limit of 20, and its current moisture content is 50. The plasticity index is 50, 20, 80, or 40.
Plasticity
I
index?
can't listen
PL
to questions.
I want 40.
Yeah, I agree.
Yeah.
Was that just the answer?
Yeah, do it.
The
Yeah.
answer's 40.
So that's equal to 40.
Man, well, okay.
Liquidity index is,
LL minus PI.
what is it?
Or, yeah, LL minus PI.
LL minus PI.
Sorry.
Wait, so liquidity index is
So you're just not in here?
That is not on here. You can't ask that question.
Invalid.
Error.
Error, error.
Syntax error.
Please recompile.
So you want to redo this?
Yeah, so PI is LL minus PI.
Liquidity index is what?
Oh,
I was right there. I was
I thought
told
there
you
was
right.
more
PI
too.
plus
That was
Something with a parenthesis.
PL.
Water content minus PL over PI.
So we're
Okay.
supposed to memorize that?
Can you just, yeah, exactly. Are we supposed to memorize that?
That's bull.
Not that hard to memorize, I guess.
Are you kidding me?
What this
This
is,
is only 15%. I have to.
we've got liquid limit,
Oh.
we got plastic limit, and we got our moisture content somewhere in between. Liquidity index is just an indication of where you are between plastic limit and liquid limit.
Oh, that makes perfect sense.
No, that's a lot better than what I was.
Well,
hoping.
PI
This-
is
this-
LL minus PO, so that's the
This
whole
here
limit.
is PI.
That makes sense.
Look at the gate.
So
That's
WC
PI.
minus PL.
Fair enough.
Okay,
Where's LI? I still don't see an LI on there.
After everything.
LI is the ratio coming from this direction, so if the moisture content's right here,
It's that to the whole lean section.
that to the whole PI value gives you an indication of what the liquidity index is. So if the moisture content was 80,
Breathe.
the moisture content was 80, so LI equals 0 is here, LI equals 1 is here.
Yeah. I'm not memorizing
Remember
it
that.
because my brain does not have capacity.
I don't use like 10% more brains
I'm good
anyway.
now.
Is that actually an example question?
Yep. I mean, that's easy, if you ask me, but I'm a geotech, so.
I'm not.
Hydraulics question, see if he thinks it's as easy as
Yeah.
these.
Use 50, not one.
I feel like you tell the freshmen that soils and foundation and geotech is most percent of the FE, they will start paying attention a lot more.
They would.
Remember, it's
I think it's just
fun.
like something.
True.
Oh, this looks fun.
That's not.
No, it's a manometer.
No, it's a piezometer, wait.
No, a piezometer is with the nozzle. No, that's a pitot tube.
Pete Dot.
Shoot, what the heck is a man?
Man, watch this video later this summer.
Nerd.
Wait, what's the mason jar?
They drink moonshine out of.
Set for a second.
The gold coat on the top.
She. Trying to say it.
A picnometer. Picnometer.
Picnometer. Oh my gosh, I forgot about this.
The mason jar.
Cute little picnometers.
That's specific.
I'm hungry.
You should not do.
My brain is.
Oh, wait.
Did.
Absolutely. Like.
My brain hurts.
This first one is,
I mean, seriously, I just.
the first one's kind of odd, but it is something they'll get you with.
It can't be.
If, you could do permeability testing, right?
Oh.
This is the permeameter. Permeameter, remember we took and had the reservoir up high, and we had, the tubes came down and it flowed through our sample, and we collected the water, it came out the
It's
end.
exactly like that.
What's
That's all
that
that
picture
is.
of then?
In an unusual format. If you want to say that. You got an upper reservoir height, you got a lower reservoir height, you got a soil sample in between. So you're taking care of calculating permeability for this. So now, but one of the odd things I'll get you, what is the length of the soil sample?
20 centimeters.
19, 20, 21, or 23?
19.
It's not 20.
Smaller than 19 if those are truly horizontal.
I have a question.
We don't know the angle.
It's 21.
Can someone tell me what this is?
How is water free on both ends and not spewing out the bottom? That's my
The
question.
soil, the permeability of the soil, it's stopping and only letting a certain amount through,
Oh, I didn't give you any.
tickling.
Woo, sorry about that.
Okay, that makes more sense now. Where'd you pull that?
Well, I just got it because it's not that skewed, so it's gotta be more than 19, it can't be 20, it must be 21, right?
Oh, it's not a bad thing. Area,
Just look at you.
Yeah,
Top
using
five.
logic.
It's all smart
Syllogisms.
over here.
That engineering judgment.
Fly to
stuff.
sleep.
That's probably
Then don't
and
sleep.
your judgment stuff's gonna be the end of you.
Why are you so mean to me?
what he's saying.
Part of the problem is calculating the area, which is not a big deal there.
I can do that. That I can make correct.
Like,
I'm
like
gonna break on that.
Sometimes. So what is the head loss from point A to point B?
120.
Head loss from point A to point B, we've got choices of 100, 120, 105, 170, 120.
Big money.
These are not geotech questions, these are hydraulics
This
questions.
is CP permeability. What is the hydraulic gradient?
the 120 was correct, right?
120?
120.
Okay, good.
The logic behind that is that 170 is too big and it's greater than 120 centimeters below. That's the rationale?
It's the difference between A and B.
It's the
Height
difference in
difference.
elevation between A and B.
The soil doesn't make any difference?
It just has-
It's a hydraulics problem, it's not a
It's
soil.
hydraulics
It's not a
problem.
tank problem, really.
At that point, it's hydraulics
Is the
problem.
soil still there?
It's still there.
All you're looking at is the real simple way you really should do it is you just set your datum right here and say 50, 20, 170 minus 50. And that's your 120 is really what you should do.
That's budget.
That's what you should
Drain
do.
it needs right now.
If that works out for you. It may not work out for you.
Plug in a drain.
Yeah.
If there's
Um,
soil in a pipe, and nobody's
The
is it still there?
pressure head at point
It's
C,
clogged.
Where is
which
the?
point C is here, point D is here.
So now those are bigger.
I guess it
Red
is here.
green point.
So the pressure head at point C is head,
centimeters.
Is,
Pressure head.
181.
pressure head,
What are our options?
100 centimeters.
pressure head, 40, 70, 100, 170.
100.
100 is just 100 centimeters, right?
Oh.
See?
Pressure head.
So I thought I had it wrong.
What's the pressure head at D?
120.
Pressure head D can be 40, 50, 0, or 100.
It's not 100. Maybe.
Could be 50.
Be 100.
0.
Would be
because
0
there's
because it's
50 of
open
the
air.
sides. Maybe.
And D?
It's 0.
Got it.
Cheater.
It's 0.
Oh, wait, okay.
See, the pressure head,
Last job.
Why is it zero?
Wait, then why would
Because it's
you
at the same height as
The
D.
same height as B.
Which
So
is
if there's water
Then-
with it.
Same height as
20.
B, which is
these two are the same height, so
Right.
it's,
But C.
You go
says
down,
C
but then
is
you also go
100,
back up,
C
so
should be
you-
then 20.
C is,
Yeah.
the water head here is 100 feet, 100 centimeters.
Right. How is that 100 but then D is 0?
Because
There's
as
only
D,
20
you're gonna go
centimeters
down to
difference.
the datum and then you're gonna go back up to D, it's gonna cancel out.
It's because the soil is 100 centimeters worth of head. Since it's so. Y'all can't understand because it's so complex.
What is the head at E?
Dirt.
In between 100 and 0.
10.
100.
110.
And I'll tell you E is in the middle.
What are our options?
Yeah.
It's not gonna be,
It's
not gonna be 110.
60,
It's
70,
50.
80, or 50?
50.
50. The pressure here is 0, pressure here is 100, it's gonna be equal to that.
Y'all gotta just do the addition.
And
Seepage.
she got me there.
See,
I still don't do it.
hydraulic gradient,
I swear, it's because the soil is 100 centimeters with the head.
hydraulic gradient.
Can we go back? I still.
It does make sense now.
That's
How is
actually what it is.
Yeah.
Think about how much more dense,
That shouldn't have any, that shouldn't have anything to do with it.
If I take this
Absolutely
water
does.
table and drop it 0.1 centimeters, what's gonna happen to the water surface right here?
it's gonna increase
It's gonna drop, I'm gonna drop it. These are gonna be the
in the
same.
negative direction.
Okay.
So if I start here and add 50, come back over here and take away 50, I'm back to 0.
Okay, so then if you go up 20, if you go down, start at B, and you go
This
down.
is soil in here. It's no longer just a pipe now. You're thinking of it like just a pipe. There's soil in here that's influencing loss of energy.
100 centimeters worth.
There's loss of energy there going through the soil. And at the midpoint, it's 50 because it was 100 here and 0 here.
I get that.
Is the soil
Just
totally
When you-
separating the two sections of water?
Isn't it totally like?
That's how it's
immovable,
act- that's how it's
immovable?
That's something that I would, the water's connected.
Is
It's
it
just
is it
saturated.
impermeable?
The pressure's decreasing as we move down through here
Yeah, I guess that's true.
to 0. We're increasing until we get to 120 or to 100.
If you want point C, just start at A instead of starting at B.
Well, I mean, I could do that, it just makes sense from point D.
Do what?
Okay.
Never mind. Move on.
What about B?
What's the hydraulic gradient in the soil? I delta H over L.
What is that?
100 divided by 20.
Oh.
It's Oh, let me give you the answers, I guess. I'll give you the answers. 0.95, 7.5, 2.86, 4.76. Now, pull that one out of your pocket without.
100 divided by 21.
4.7.
Okay, thank you.
What's 100 by what now?
100 divided by 21. Change in head is 100. L.
What's that calculate to be?
4.76.
4.7.
Changing H.
That's not it.
What?
We just established that there was a drop.
Delta H over L. What's the change in head
100.
across the soil sample?
100.
100.
Divided by 21.
L was 21.
L is 21, I'll give you that much.
Okay,
The
it's
change in head was
21
100. We just
over,
set that, didn't we?
Yeah. Say it was 100.
D is
oh,
100.
oh, it's 20 over 21. Whatever that is.
No.
No.
That's
0.95?
the 0.95. That's a plausible distraction.
Consider myself.
The 120, 120 divided by 20.
Why?
Yes.
120 divided by
That's
20.
not the answer, though.
That is the answer.
That's not an option.
That is-
It's 5.7. You're either like stick figure that one's wrong.
Oh, yeah.
I was right.
Less Dixie.
Oh, sorry about that.
I between where?
Why is it 120?
Because it's the difference between A and B.
H is
Because it goes
120.
So
down.
that's 7.5 is a
50
probable
again, so it's
distractor.
20.
Down 50, up 50. I'll just zero it
Down,
down.
okay.
I is the change in energy from that surface to that surface.
Which is, it's
That's-
100.
yeah.
Which we said.
And we said C is 100, D is 0. So it's 100.
No.
What's L?
No.
Did we or did we
L
not
is-
say
L
that?
is-
L is 21.
Up there.
21, we'll get that up
He
there.
said I is the change in energy, but delta H is the change in head, not
Yes.
energy.
Okay, we established the change in head from C to D is 100.
We did.
It's 100
We
centimeters.
said that already.
How is that 120 now?
We said earlier, C, because when we calculated E, it was 50. Because
You go down 100, go down 20, go down 50, and then go back up 50 again.
So that's
I thought you just had strings on us all.
Because
Can you
that's
read the question?
One does the.
The hydraulic gradient
No, no,
is.
no. From A
Yeah,
down
hydraulic
to,
gradient,
it's a bottom, you want to back up 50.
Yeah, that's gonna be a
And
review.
that's just in A and D.
And yeah. This is for right fluid mechanics, straight
Why
up.
are you going back up?
Because they go back up.
It says
you're
right
going
here,
over.
delta
Yes.
H over
Yes.
delta L parallel to flow in the manual. Does that help in any way?
Well,
Parallel to
then when they
flow?
talk about parallel to flow, they're talking
That's
about
right,
the 21, put the phosphate on there.
Oh, there it goes.
Please explain why delta H is 120.
Kyle, it's between A and D, not C.
I-
Change
Yeah,
in
but
head
people were
between
talking
this
very
point
calm.
and this point is what?
That's 120.
200.
I don't get why you don't just take into account just this, where it's the soil.
Yeah, I don't either.
I feel like that's usually what we always do.
Just where the soil is.
The change in head. The change in head would be 0, wouldn't it? From A to D, because at D you have 0, right? That's 0.
You have zero pressure right here.
Yeah, so at A you have 0 as
And
well.
from this point
From A
up,
to B.
from that point to here, what do you have?
The change in head from A to B is what
Well,
you're
you
talking
increase 100, then you decrease.
Yeah, it's either a path or a state function. I don't know. It'd be 0 from A to D.
No, from A
No.
to B.
From A to B is 120, the delta, the
Pressure
Oh, wait.
is 0. The
120.
difference is 120.
Well, you said the pressure D is 0.
Yeah.
We know the pressure A has to be 0.
And so is it at B.
But not, the pressure, yeah.
But
not
it's the
delta
pressure on the
H.
head.
delta H.
Change in head.
Well, that's what
not-
we're talking, somebody's talking about two different things.
It's
You're
height.
talking about pressure.
Yeah,
I don't know why
not
not
pressure.
Talking about delta H.
I want to know why delta H is 120.
What's the difference? What's the difference between pressure and head?
I want to hear.
And I'll
Isn't
draw
head
it
just a
nice and
measure
good for you.
of
Yeah, it should
pressure?
be off by. I'll draw it up nice and good for you.
9.8.
And we'll get it back out. The next question, the velocity in centimeters per second. And our choices are 0.1117, 0.0057, 0.00286, 0.00476.
Are we giving a K
This,
value?
this is actually going to be equal to 5.7 centimeters per second. So what's the velocity?
Were we giving a K value?
Yes, you were given a K value.
Thank you, we need it.
It's moving very
That's a
slowly.
good test for you, although, yeah, it said in the problem statement, sorry.
Because there is a higher pressure at A than B. So eventually the water will move towards B.
Atmospheric pressure is the same for both, this is an old thing.
So,
Pressure has
so
nothing
what
to
is
do with-
velocity?
K times I.
Velocity Ki.
Dang, you're so smart.
It's right here.
So there's,
I knew that.
there's I, there's K.
It was given immediately.
Oh.
It appeared out of nowhere.
We just wrote it down. It's a 5.
I is our 5.7. Yeah, I can do that math.
All right. I think we just lost that. Just lost. Compaction.
Is that sandwich here so I can
Say what the
compact it
total
into
head
my
of
mouth?
this is sediment, use like this.
A Proctor compaction test in the laboratory on a borrowed pit
Because the whole system is used.
gives a maximum dry unit weight in the D max
Whole system is
of
used.
19
That's-
kilonewtons per meter cubed
I want to know.
and an optimum moisture content
Be happy to know.
of 10%. The bulk unit weight and moisture content of the soil in the borrow.
What the heck is a borrow?
The bulk unit weight and moisture content of the soil in the borrowed pit, the actual
What is this? Is the
is 117 kilonewtons per meters cubed, and moisture content's 5%. So this is the natural condition in the ground. This is from a Proctor test.
What's the moisture weight? It's 17 or more.
Moisture weight 17 kilonewtons per meter cubed. A highway fill is to be constructed using this soil. The spec requirements for the fill shall be compacted to 95%. %, standard Proctor. First question. Let me flip up my sheet here. Is how many cubic meters of borrowed material is needed for 1 cubic meter of highway fill? How many cubic meters of borrowed materials? How much do I have to get out of the pit? So I've got a pit here. I'm gonna dig soil out of, so I can bring it over here and build my embankment. When it goes in over here, it's 95% gamma D max. When it's in the ground over here, gamma M 17 kilonewtons per meters cubed. So we need to figure out what our placement density is. Right? What's our placement density going to be? It's going to be 95% of gamma D max. We gave you gamma D max. So this is 95% times the 19 kilonewtons per meter cubed. Ends up being 18.1 kilonewtons per meter cubed. So question number 1, here again asks how many cubic meters of borrow do we have to borrow? to actually end up with a cubic meter.
1.17.
How do we get that? How do we get
Rate
that?
V1 gamma 1 equals V2 gamma 2. You have to find
B1, gamma 1, B2, gamma 2.
95% of gamma D max, 18.05. Multiply that by the moisture content, you get gamma M of the 95% compacted material, 19.85 kilograms per cubic meter. You just plug that in your ratio.
Say that again.
V1 is what you're finding.
So this is, we'll say that's the fill.
Yeah. Gamma 1 is the 17 of the field.
17 of the fill?
Oh, I like that.
That's your moisture.
Okay, you're on a different side of me. That's the 19.85.
Where's 19.85 come from?
19.85 is the moisture unit weight of gamma D of 18.5, which is 95% of 19. I just did it right here.
Yeah, that makes sense.
I mean, I believe
19 times 0.95 gives you 18.05.
All right, 18.1, okay.
Multiply that by moisture content, multiply by 1.1, gives you 19.855. So,
Why are you multiplying? Does it have to be the same time again?
What do we always want to work with in soil mechanics? Dry unit weights, weight of solids.
You gotta find the dry unit weight of the material you're
But
given, the
you're-
moist one. Yeah. And then
So
figure out the
we need to know
volume
what,
you
we need
need.
to know what dry unit weight this is, right?
you divide it by 1.05.
So gamma D here is gamma M over 1 plus the moisture content. So that's the 17 over the 0.05. That's going to tell us it's 16.2 kilonewtons per meter cubed. That's the dry unit weight from the borrow. So you're in the right direction, but you just didn't need the moisture unit weight in there.
I mean, it still works. It's still the same answer. Did it? It did. No, it didn't.
So gamma D required, or the gamma D of the fill, or with gamma D borrowed.
Yeah, it's 1.1. I'm sorry. 1.12.
Is it different when you do the moist?
Yes. Yes.
When I did the moist, I got
One of
1.1.
those.
Yeah.
That 1.17 is the answer yet here.
Yeah.
They would've got him. They would've got him. Would've got him. Let's see here, the water content at 95% compaction. The water content, gamma D 95%.
Whatever answer.
The moisture content at 95%
Essentially, yes.
is 9% on the dry side and 12% on the wet side. What is the minimum additional weight of water per volume to achieve 95% Proctor compaction? Answers are 0.8, 1.63, 1.2, 0.82.
What
So
class, may I ask what class is this from?
What's that?
What class is this from?
Soil mechanics.
So you're saying we're at 5% water content?
We're at
what
5%
we need
over
to
here.
add?
We're at 5% on this side,
So we know.
and we need to be either 9%
9, 12.
to 12%. So what's the minimum we need to add to get essentially what we're looking at to get to 9%, right?
We know it has.
Kilonewtons of water, is that?
Kilonewtons of water, what we're looking for.
2 inches out already.
Kilonewtons of water.
You know, we can't have more than one.
Say it again?
Can't have more than 1 point something, because that'll put you over, right?
But we know what our our dry unit weight is, right?
Yeah, 16.2.
So 18.1, right? So we need 9% water. 9% water is going to be, so the weight of water required, we'll call it, is the gamma D of 95 times the water content of 95. 18.1 times the 0.09 is 1.63 kilonewtons per meter cubed. So that's how much water I need in a cubic meter. I need 9% of the 18, because that's the dry, because that's our control point. So we need 1.63 kilonewtons per meter cubed of water in our fill when we're done. How much water do we have in our fill?
5%.
We have 5% of,
So if you
5% of what?
17.
Kilonewtons.
Or no, 16.2.
Water contents.
Sure.
Is the volume of water, or the volume, or the weight of water, or the weight of solids. So we know what this is, 5%, right? We know what weight of solids is. Remember, we got to deal with the dry.
So it's 17 minus that.
So this value here is 16.2. We solve for weight of water, which is these two multiplied together, and we come up with 0.81 kilonewtons per meter cubed is the weight of water we have. The difference is how much water we need to add once we take it to the fill site. We got to add that much water to get our moisture content up.
Wait, our water content is derived from the weight of the solids?
Always weight of solids. It's the secret to soil mechanics.
It's
It's
probably
the dry
much
weight of
more.
solids, because that's a constant for us. That never changes. We pick up 1 pound of dry soil, no matter what we do to it, it's always 1 pound of dry soil. We can add 10 pounds of water to it, or 20 pounds of water to it, or any pound of water to it, and that's going to change the moisture unit weight, because moisture unit weight has wet and dry in it. But it always has 1 pound of dry soil. That's the key in soil mechanics.
Yeah.
Weight of solids.
So what's the answer?
Weight of solids.
82.
It's this one, the difference.
Yeah.
The difference there.
Wait, did you get 0.81?
That's the
You have to
weight
have
of
the
water.
difference between the necessity
So that's
and
the
what you
volume,
have.
16 minus 0.81.
That's the weight of the water.
Well, I got 1 out of, what would we do, like 8?
Surely we'll all get this one right.
I really dislike when you say that.
Makes me feel really bad about myself.
You are like full-fledged PE. We're taking the FE right now.
No.
Yes.
Yes.
That is a little bit on the heavy side for an FE exam. I agree. But these are the example problems we got, so let's work them. But the next one's an effective stress problem.
All right. What's effective
They all feel more
stress?
confident already.
Is that right? Effective stress is sigma?
Sigma? Herbert equals nerd. That's on this list, right? Herbert equals nerd.
Purple equals air.
Herbert equals nerd. PV equals NRT.
PV equals air.
Oh, no. Sound.
That was,
Prime is equal to sigma minus equal.
What do you? Oh,
that's
okay.
peer pressure.
Effective stress.
Would you like a beer?
Thermal stress minus, yes, I would.
The effective stress at point B
Oh, this is
is
just
16.4,
gamma H.
36, 18,
36.
19.6.
Very good.
Point B.
Is that soil between A and B?
Yes, it's the same. I'm sorry. I-
The water table is at B.
Water table is big, so.
Okay.
So it should just,
It should be times
18
2 times
times
18.
18 times 2.
So what do you want, the effective?
Yes.
18
But so that
times
gives
2
you
is 36.
kilonewtons per meter.
36, right?
36.
So it's gonna be 36, right?
Should be delta H, isn't
2 times 18
It's the same.
is 36.
it? Oh,
If you were doing from like B to C, then that would matter.
What's the pour water pressure at C?
So that would
Like
be
30.
Point C, we can have 39.2,
4 times
58.8,
64.2.
19.6, or 20. So this one was,
39.2.
No, pour water is just the water pressure. Just the pressure due to water, not the soil, right?
39.2. Please tell us I'm wrong. I will.
NW,
call Z or what we want to call it.
yeah.
I'm going to take my own Z right now going from here.
4 times 20.
9.81 times 4,
Which is
39.2.
This is smart.
Oh man, I kept doing American. American.
Man, that's on tape.
That's on tape,
Said Kennedy.
What's the effective stress?
What?
Said Michael Kennedy.
Said Michael Kennedy.
Oh, yeah.
Not Chris.
I said worse.
The effective stress
Him right
is
there,
C.
American units.
1116, 76.8, 80, 98. Effective stress at point C.
So you get answer B plus 1 times 20 plus 4 times 9.1. I don't calculate.
76 point.
Oh, I'm sorry. Back, go. Total stress.
Oh, the plot.
Not ready for effective stress yet, total stress.
Oh, man. No.
Minus the water.
It's 2 times
It's
18
82 times
plus 4
minus
times
water.
20.
Plus 4 times
so
that.
that's
Danielle is here. Danielle is. Run.
18 plus
Stop
4 meters.
So take American.
20. What's that count? Should be 116.
Yeah.
Oh, the prime was 76 point.
Yeah, this is total.
This is why I'm gonna fail.
And so then, as we all know, we're going for the effective stress. We got a 116, 76.8, an 80, or a 98. Effective stress is total stress minus pour water pressure. So we already got the problem solved, right? 116 minus 39.2, correct? Well, if you want, that's not a bad way going for it, I guess. 76.8. I mean, that's a realistic problem right there.
I like that one.
Shut it down. Shut it.
We got 1 out of 3.
Problem number 12 is the same problem essentially.
Food's here, we just make 3.
No, let's keep going.
Keep
Oh my God.
Is the food here?
Yeah.
We can eat more.
Go ahead and,
We have to get our food first.
because I got a flow net to draw, so I can take a second while you guys get the food.
Stop.
Oh, yeah.
Very thin.
You are professional.
Do perfect.
Okay.
Maybe can you see me from here? I think I'm sitting like this the rest of the class.
No, it
Can you see
cannot.
me?
No, it cannot. It can see the top of Kennedy and from the torso up of Nate and all of Zion,
All right.
even his feet.
Some of these ought to be boom, 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 boom. How many head drops are there?
4.
There are 4 flow nets, flow channels.
How many head drops are there? Question number 1.
1, 2.
It's easier to count the other way.
12's not one of the options.
Yeah, there are 12, but I think
Oh.
it's 13.
Yeah.
Now it's
You know the
13.
line.
That.
Just an arrow.
Oh my gosh.
Wait, what?
I got
Oh, there's
4 drawn
14?
flow net here.
14.
Okay.
Now
There's actually 14.
Yeah, you're in front.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14.
Okay, yeah.
I said, I'm not drawing long enough, so it's out of proportion. How many flow channels are there?
4.
1, 2, 3, 4.
Best thing to do is get in the center of the structure. 1, 2, 3, 4. What is the total head loss across the site? Across the band?
700 centimeters,
7 meters.
Let me,
but it's in centimeters.
This is another
She's right.
right, it doesn't really show it,
I guess it's,
but it's implied, I think, that this does like this.
Okay.
that's
7.
700.
So we're talking 7, right?
100.
So if your datum's right here, this is 0, 7,
It's on the right.
and it says in centimeters on the.
Those jerks.
Yeah, on the right side you have ground and water on the same level.
Yep,
Okay.
can be. Can be.
I'm serious.
Can be delta, little delta H, head loss per head drop. Head loss per head drop,
700 over 14.
700 over 14.
50.
I got it first.
They did.
Yeah.
Is that something that's usable or just a strange thing to ask?
Now you
It's
can
in one of the
determine
books.
it.
This, you need this
Okay.
to solve pressures. You need it to solve pressures. Q,
Q. What is it?
KIA.
1 times 10 to the minus 5th centimeter per second.
Do you have a K value?
A times H
K is
Yes,
1
K
unit.
times H.
times 14 over 4.
K times what?
H.
H.
How about delta H?
Delta H 4. K I A.
M sub F over M sub D. You got K was given to us, 1 times 10 to the minus 5th. Delta H is this total head loss, 7 meters. M sub F is 4.
0.02.
17.02.
So this equation is not given.
Yes, it is in there
Yes, it
somewhere.
is. Somewhere.
It is in there somewhere.
First page.
First page?
Q.
Oh, gotcha.
Now is when a little bit of challenge comes in.
Oh, boy, for pressure.
What is the pore pressure at A?
We use the 3 potential drop. That H would be times H, which is.
So maybe we use of A is H minus number of drops times the little delta H.
150 to 15. So, all drops is 3.
And this really would have started out with the gamma W right here, right? But we're gonna not put him over here and put him over here. The H is 7. That's the headwater. It's not the difference, although it is the facts and it's the same thing here. It's the headwater. What's the pressure at this first equal potential drop? So this is 7 meters minus 3 drops, 1 drop, 2 drops, 3 drops. And there is 500 centimeters per drop.
50.
50. And we'll call that times 9.81.
How about units?
We don't like units.
You want that?
Yeah, meters and, okay.
This is meters
I
here.
got it.
This is kilonewtons per meter cubed. This is 54 kilonewtons per meters squared. Pore pressure B is the same thing. The 7 times 1 drop, 2, 3, 4, 5, 6 drops. So we have 6 in here instead. And that would be the only difference, used to be.
Now surely they're gonna give us, if they ask for pressures at the locations, be right on the lines.
Doesn't matter.
Well,
Doesn't matter. One, C.
well then you're gonna be judging if that's exactly, I mean, surely they're not gonna be that.
Surely if they're gonna make you judge that that is 0.5, that you're not gonna have answers that are 38, 39, and 40.
Yeah, I was, okay.
They're gonna have answers that are 54, 29, or drastically different.
Okay, good.
Drastically different.
ND would be 6.5.
What's that now?
So ND would be 6.5.
Yes, yes, yes. Because really and truly, if I wanted to make this thing more and more and more and more complicated, I could draw another flow net down through here. But when I do that, I get out of sync, so then I have to draw more flow channels, and more flow nets, more channels. The secret's to getting that ratio the same. If you draw everything correctly with your circles and your right angles and all that kind of stuff, you could have 14/4, or you could have 28/8. As long as that ratio is the same, this ratio is always the same.
14/4 and 20/8 are not the same ratio.
28/8.
Okay.
28/8. So as long as that ratio is the same, this equation always comes out the same. It's just how much time you want to spend drawing flow nets. I guess we could have done 2/7. Still got the same value out of it, because this is still always the same ratio. The head water height doubles. So somehow I go in here and put me a little extender on here and fit this up to 14 meters. How did I rephrase that? The increased blank by 60%. The blank increased by 60%. The flow remains the same. The flow is halved, or the flow is doubled.
What's blank?
So
Is the increased and the blank backwards?
it's just an ABC.
The blank increased by, yeah, the blank
You
increase.
can do it either way, I guess. They have it in the front.
Yeah, what is
So-
the dollar sign?
Blank increased by 60%, the flow remained the same, the flow halved, or the flow doubled. When H doubles.
Flow double.
Double, because delta H doubled, right? Delta H was 7, and now delta H is 14. Well, you double that value, you'll double Q, right? Double the value, double Q.
Flow rate.
Flow's double.
Increase.
If the sheet pile was extended, the length of the sheet pile was increased.
The flow rate of.
So we extend the sheet pile on the ground a little farther, did the flow increase, decrease, stay the same, or it's indeterminate?
Indeterminate.
Yeah.
What's the question?
The sheet pile.
The sheet pile length was increased.
It'll
So I
change
increased this
Flow.
to 4 meters in the ground,
What are we asking if it's increased or decreased now?
the flow.
It'll change your flow net.
Decrease.
Yeah.
It should remain the same, you'll still have the same number of drops on it.
You still have
It
the same
changes your
ratio.
flow net if you
It
increase
changes
the
your flow
length.
net.
Changes your flow net.
So you don't know. Gotta draw a whole new flow net.
Yeah, it's true.
You have the capability to draw the flow net.
Not during this exam, I don't.
Intuitively. Flow increase, decrease, stay the same,
I think it was
Decrease.
decrease. But when you go to draw a flow net now through there, you're gonna have less flow channels and probably just very nearly the same drops.
It's indeterminate how much of time.
So
Yeah.
it's actually gonna decrease. Now you can't just come out with a number unless you draw a new flow net. You just draw a new flow net.
Ain't nobody got time to flow now.
You don't have time to draw a flow net.
Like we're.
Keep that graph.
Oh, yeah. Okay. Did I tell you about the turkey? Nobody can fit it, man.
Did you just throw something across the room?
I flipped it at Kyle and it worked. It's not
That works about Thursday.
Friday?
Oh, looks like a banker today.
Oh, it actually.
Looks like a banker today.
It looks-
nice and purple color.
He looks like a baker.
You go back and then.
I mean, love the bill.
Looks like just an awesome.
There's a banker would have closed like 12 hours ago.
If he had longer hair, he looked like American Psycho.
What did you say?
I said if he had longer hair, he looked like American Psycho.
For the void ratio, vertical stress, or E log P, or from a consolidation test, the compression index, C sub C, is equal to
Oh, I know this, hold on.
0.397, 0.400, 0.040,
Sitting there.
0.003. C sub C equals what? What is C sub C?
Coefficient of.
The slope of that last
Patch.
section,
Coefficient what?
Cavity?
compression
Or curvature?
index.
Wrong C sub C value. Yes, C sub C is
Concavity.
coefficient of curvature, but that's for a gradation curve analysis.
Oh, it's right how you
We're
get it.
talking about
Compression
settlement
index.
analysis.
It's the slope of that line.
Slope?
C sub C is the slope of this line right here, right?
What's the?
Is the line, the coefficient C being
0.009 L minus, 10.
compressibility. What's that?
0.009 times, I keep forgetting.
I got 0.4.
L minus 10.
0.09.
0.009, what?
C
How
sub
about
C.
0.4?
Elderly would limit the shortcut method is what she's going on.
Rise over run.
No.
If you did the
0.4
graph,
divided by 900.
Quick.
It's 0.4.
0.4 over 900.
No, it's the log 100 minus the log 1000.
Oh.
So it's 0.4.
No, that's just a log scale.
This is log scale down here, right?
So it's 100 to 1,000, right?
So you
Yeah.
pick 2 points,
I'm not getting any of that.
take 2 points, right? Make the difference in your E values over the difference in your log values.
If you do 9,
I got 0.0004.
I get 0.4 if you do log 100 minus the log 1000, which is what I saw in the slide, I think.
Slope.
I think you did that.
Is that correct? Ah, you're shaking your head, so that's yes.
Actually, this is actually.
Ah, boom.
Now, the easy way of getting it, and they did this for you on purpose, the log
0.6.
over magnitude, the difference is equal to 1. Is equal to 1. So real quickly, when I see this, I say, I go 1 log cycle, I find my 2 values, so it ends up being 1 minus 0.6. E is, delta E is 0.4. 1 minus 0.6, because that's over 1 log cycle. Makes it simple, makes it easy. Makes it simple, makes it easy.
2 log cycles to.
So if it was 2 log cycle, it'd be 2 minus 0.6?
Log of 100
If it was
minus
2
the
log
of
cycles,
1000.
it'd be 2 minus 0.6?
So I guess it's
So the one from 10 to 1,000?
No, you only go over 1 log cycle.
If it was. If it went from 10 to 1,000 instead of 100 to 1,000, that'd be 2 log cycles.
Now you still want to just pick 1 log cycle to do your work.
I know.
It's a back.
For
Okay,
example.
that makes sense. No, he's saying that you would always do 1 log cycle.
You always want 1 log cycle down here, so you want 1, that gives you 1 in the
You
denominator.
just split the line in half or whatever.
Right.
Right, what I'm saying is say that slope, where it goes from 100 to 1,000, say for example that slope went from 10 to 1,000.
So get rid of all
That'd
that.
be just be
No,
two.
because here it goes.
No.
No, the C.
It'd be 0.4 over 2, which would be 0.0 or
If
0.2.
you
Oh,
didn't
from
know
here
that-
to
if
up
you
here.
didn't know
That's
that
2
you-
log
Yeah.
cycles, so that's
But it's
2.
one line.
1 line, so this goes from here to here,
Yeah.
and this crosses at
Exactly.
Yeah.
0.8, and we'll take 0.8 minus 0.6, I got 0.2.
Oh, okay.
Because my slope of the line's flatter, right? What about C sub R? Or C sub S?
That's the
Recent
upper
expression.
line.
Top line? C sub S or C sub R?
It's C
Same
divided
R.
by 6.
Same thing, technically.
It's 1 minus 0.2.
It's
See,
0.06.
1.2 minus 1 over log 100.
0.4 divided by 6.
0.066.
Do it the easy way.
The slope of this line is C sub R right here.
Oh, wait a second.
No, it's
No,
not.
it's not.
No.
Yes, it is.
Hold on, not on the table.
Blasphemy.
I approve.
Where is it saying it's up here?
Yes.
Oh, yeah.
This line and this line be parallel.
Okay.
In the real world, these lines will be parallel.
That was the biggest I've ever seen.
Yes, sir.
I mean, I'm confused, why are there two lines though on this, like we don't.
Say,
There's two lines.
The bottom one wasn't originally there.
this one here, you mean?
No.
Where you have
This
C
one?
sub R.
Yeah.
That's on there, that's equal. Actually, when we ran the test, let me get some of this back off right now. Just back. So when we ran the test, we loaded and loaded and loaded, took our readings, and it generated this curve. We got to this point, and we started unloading,
I got it.
and it came back like that, and we stopped the
Just
test.
because in the book, on the general diagram, it doesn't show.
Doesn't show a back line.
So, and I don't have it drawn with the scale, but this line and this line will be the same.
I just didn't have this on.
I love you guys, right?
I love it though. Because we can't say it's no, it's top line, and then he was keeping it secret that they were parallel. And he's kind of- Yeah, but that was his.
So the initial void ratio,
I won't forget it now.
So the answer to C sub R is that, is it 0.4 divided by 6, right?
it's one log cycle,
What's the answer?
one log cycle, 0.04, right? What the difference between these two now?
What if that back line isn't there and you have?
What?
Why is it not
Should be 0.2.
over?
It's 0.2.
0.6.
It's
1
0.06.
minus 0.2.
If they're parallel, it should be
0.04 minus
0.2.
0.06 is the difference between that point and that point, right?
Well, I know, it should be the same as the top one then.
If they're parallel,
Wait.
they be parallel, Jessica.
Well, I don't have it drawn very good, sorry. I don't have it drawn very good.
Well, how come, I mean, this
Yeah,
says,
that makes sense.
go ahead.
Okay. One half, okay, the slope of the top line is half of the slope of the bottom line. Because the y values, this by, one is by 0.0.
If a man can draw really good, this would actually show.
Well, that's-
This thing says.
From 10 to 100 should be 1 as well, right? So from point
The worst chips of ever.
2,
Thanks,
He has a
Kyle.
life scale as well. So, but why is it not CCC over 6?
That's what I'm trying to ask, but people keep cutting me off.
Are you talking Michael? What?
I've asked it 3 times.
Hi, would you say something?
Hello?
Hello?
It's actually bad drafting here, it's that point right there.
Oh, so we
Every
can't,
time if you project that line out, it will give you the 0.0.
so we can't do
Big
that.
difference.
Why is it not C sub C over 6?
Yeah.
That's a good approximation, but you have data. If you have data, use data, right? But if you didn't have this value, say you got C sub C of 0.009 times liquid limit minus 10, and then somebody says, oh, we need a C sub R value. Then you could do C sub R against that, so that's 6
I don't
to
know why it's
10.
not there.
So, but you got data, so use
Thank you,
it.
sir. Wow, that's
But
mighty kind of you.
C sub R is 0.2
Oh, well, okay. I'll get mine
in
later.
reality, right?
No, it's 0.1 based
Or
on.
it's 0.1 based on,
Yeah.
yeah, it's 0.1. That is nowhere near 0.06.
Well, it's it could
I mean,
be
if
6
you round it
to,
up, yeah.
it could be 6 to 10, so.
I mean,
and
yeah,
it's
but
approximation.
these are small numbers we're dealing with, so you don't round up that much.
It's approximation now.
Thank you.
That's a
You got data, you got data.
That's like an
Okay.
80% difference.
That's a, yeah.
Let's see here now.
Charles, what does that look?
That's my, your Michael Kennedy.
Oh, he just called you Michael Kennedy.
Darn.
Ouch.
What am I gonna do?
Brutal look. This is not even a game look.
Yeah, the initial void ratio, E naught is 0.6. And the existing average effective stress, that's gonna be a sigma naught value. The stress as of today, right this second, sigma naught, is 1,000 kPa And we're gonna put a fill on top, so let's do some diagram. Here's our soil surface, and we're looking at a point around here. This value is 1,000 kPa. And we're going to put a fill on top of here. Kind of soil fill on top of that. This causes an increase at this same elevation of 120 kPa. The settlement in millimeters, gas in millimeters, equals what? And our choices are 15.5, 18.0, 23.8, 12.5. Settlement problem. Settlement problem. Right? So what's the equation we want to use for settlement?
Ultimate consolidation settlement, is that right?
Consolidation settlement.
Yeah, definitely. Sigma or epsilon 2.
Strain times E times.
Remember the three different
What's the
setups we had?
This is not even anything else.
You just gotta.
What? What?
Shoot.
Remember we had the three settlement equations? We have one settlement equation that would move us from here to this region. We have one that moves us down to the C line. Or we had one combination equation that went all the way down through there. Remember that?
Now, do they give us, like, like when you use which equation?
Do what now?
Do they give us like when you use which equation?
No, you have to,
I mean, you got primary, secondary,
or you got normally consolidated over consolidated.
yeah.
Yeah. So in this particular case, it's a normally consolidated situation.
Full.
It didn't actually state it. But
But
it didn't give you a piece of P, a sigma P value. So you don't know what this value is. You don't know what that value is. So if you don't know that, safe assumption, and they're probably just gonna work in this region. Dealing with a consolidated settlement, I don't think they're gonna get that on this kind of exam.
Well, we don't even have the equations.
Yeah, I can't find it.
Yeah.
They don't have the equations for that in there?
Yeah, so there's no way.
They do, CDHS.
What happened to just like solving for X? Okay. If X was.
I think this is all just like different equations, so easy.
Yeah, definitely. 8 hours of plot transforms.
See you, Charles.
Bye, Charles.
Bye, Charles. Bye,
See ya.
Charles.
See ya.
Let's not stay till the end.
Yeah.
He acts like he has a meeting, but I think he's lying.
Yeah, he doesn't have
Give it
any.
half an hour.
He has a meeting, but he's in jeans. I mean, come
He's
on.
got.
Oh, y'all shut up. Get that on camera, shut up.
Good night, Charles.
Later.
Love you.
I don't see it in the supply reference here, do
I do not.
I? You would think they would have.
And you say that was in your update review material? Am I on here?
That's a lot of numbers.
No, that's not.
It's not present on
How are you
No,
Why didn't you tell me?
That's dealing with.
I thought
That's why I saw. Okay. I
I
heard
was
this.
talking to you loud and he's laughing at me. I
I
didn't know what he was
Well, I
looking at me for
remember
eating
something
my
from
cheese.
class.
I didn't know
You
he
need
was
to tell me to
laughing at
remember
me.
something. It's the same way you do that.
I remember that, but I also remember there's like 3 equations to choose from.
There's three
You
equations.
looked over
to
at her.
choose from. They all have
No.
They're all very similar.
You looked over at her. You both laughed. So I was like,
So that's hard to remember.
This is the only one I think they're gonna, like I said, I don't think they're gonna bring over consolidated fee on this exam. That's the one that you try to remember if you don't remember something.
I know that's the one I use in foundation, but it's,
Because C sub C, we just had from the last problem.
You know what?
H is the thickness.
Which was not given.
Well, we're referring back to the last problem.
See previous drop.
You know, they didn't give us a thickness.
Can you solve it by this ultimate consolidation settlement using
We
epsilon?
could also just look at,
Are we still doing a problem which we had when?
But it's not what it's giving you. Does everybody get that? Delta E total?
oh, yeah, the soil's 1,000 millimeters thick. It's given. If the soil, what's the settlement of millimeters? If the soil thickness is 1,000 millimeters. So now, what value of H do we use then? Do we use the full thickness, or we use half the thickness, or we're doing quantity, so it's the full thickness. Quantity is the full thickness, so that's that value right there.
Okay.
That gave us E naught. The initial stress they gave us is 1,000. The change in stress they gave us is 120. 1,000 on the bottom. Crunch and run, you come up with,
Where do we get this?
C to C is 0.4 from the previous one.
Alright. Why the heck is that?
When was it that you used a different H again?
in the next problem.
Wow.
In the next problem.
Now you know that piece. So here's my point. Okay, I'm gonna cross off the two obvious answers that are wrong. I'm gonna go through the problem, find the answer that I use already, cross that one off, and then pick the one. I got 100.
Use the total thickness when you're doing the quantity of settlement. You use your drainage length if you're doing the time rate settlement. Problem is, so we got a soil layer. It's 1 meter thick. It is drained from the top and the bottom. It is estimated that the total settlement will be 50 millimeters. If the coefficient of consolidation 0.02 meters squared per day. First one, time factor for 50% consolidation equals 0.197, 0.5, 0.848, 0.9. It's one of those I told you to memorize, right? Time factor, that's where we go to that table. Percentage consolidation of 50%. See our time factor is. The time factor for 90% consolidation.
0.848.
So this is the one for 90. So those are the two values I told we all typically always use. You just got two problems, just that quick. Just that quick. Estimate the time in days for 90% settlement. Parentheses, 90% consolidation is the same as 90% settlement. Parentheses. So what is the time? For 90%. Our choices are 211 days, 422 days, 100 days, or 106. So what is that in days? Remember you got the time factor equation in there, correct? Time factor at 90, C sub B, T90, HDR squared.
106.
So, what all do we know? We know T90, 0.848. We know C sub B is 0.002. We don't know T90. HDR, what's HDR?
Half.
Double drainage, right? So we're going drainage top and bottom. So that silt particle can go that way or that way for its longest drainage path.
This is what I was okay with it.
0.5 meters. So we got 0.5 meters. And then we got a T90. So this is how long it takes to get 90% consolidation.
Squared.
106.
And comes out to be 106 days.
So what is actually making it consolidate?
Building.
They're telling us that it's going to consolidate.
Self-consolidation?
They're telling it's going to consolidate. They're not asking us to calculate how much or why it consolidated.
Okay.
This is time rate.
Mm-hmm.
We could have said, well, we're going to put a fill on top of here, and then we could have calculated the settlement.
That would be one way, right?
That's one part of it. Calculate how much settlement, and then you want to know how fast is it going to occur. It's going to occur in 30 days, 60 days, 2 years. So it's a time rate. So if this bottom layer ended up being rock,
It'd be 1 liter.
if one of the drainage boundaries was blocked, how much would it take the soil to achieve 90%? 1 times, 2 times, 3 times, 4 times.
Twice.
4 times.
Oh, because it's squared. That's right.
It's 4 times. Because of the square, you go into the full length and you get the square in now. So that's why when we put like vertical drains in a clay, if we wanted this to consolidate and had 106 days with a drainage path that's the 1/2 meter, if I could come in here and put in wick drains or something like that and put them on 1/2 meter spacings, then this particle of water here could go this way or this way. And if these are 1/2 meter apart, then this is 0.25. So by doing that, I just dropped that by a factor of 4. So that's one of the reasons why we would put wick drains in or sand drains in on a job site, because it drastically, very quickly reduced. If this thickness was 30 feet, and I put wick drains in on 5-foot spacings, I took it from 30 to 5 feet. I mean, you got a drastic reduction in time because the water can get out faster. So that's a real world application. The liquid limit of a soil is 50. The compressibility index is
0.009 times 10.
We're so ridiculously fast.
36.36. 0.36. That's pretty simple, pretty quick.
What did he ask?
What is C sub D?
C sub C, given liquid limit,
C, I'm sorry.
liquid limit equals 50.
0.009 times that.
What's C sub C? 0.009 times the liquid limit minus 10. A good approximation.
You've been studying.
I
0.36.
did a couple problems.
He's been grading soil mechanics homework. That's what he's been doing.
That's my bad. That's,
Oh, man.
it's amazing.
It helps to take it the second time, doesn't it?
Yeah, it does.
Oh, there it is. Page 135.
Chris over here is like a statics and dynamics wizard.
Oh, God.
Math magician.
Obviously, we all have those traits.
Bearing capacity.
That's right. I can arm wrestle pretty good.
A shallow footing
On camera?
with 2 feet, so ground surface. Do I need to switch markers? We got footing in the ground. Way out of scale here, 2 meters. Located 1 meter below the ground surface. In a sand deposit. N sub Q, oh boy, they even give you N sub Q values, that's cheap. N sub Q is 30, N gamma 40, gamma is 18 kilonewtons per meter cubed. The groundwater level is 5 meters.
So you're looking for the what? The Q ultimates?
The groundwater, so first question, the ultimate bearing capacity,
Oh, wait a second.
QULT.
Now,
I got 1980,
there's a trick to this one.
1800,
Let's see what the B.
1530, 1260. So what are we doing to do bearing capacity problem?
Just Q ultimate equation.
Q ultimate is,
C, N sub C, plus gamma apostrophe. I know. I'm
We need
okay.
to know second.
B sub F, N sub Q,
D sub F,
yep, B sub F, N sub Q,
Q plus,
plus 1/2, gamma apostrophe, B, N, gamma.
okay.
C cancels out, dot disappears.
We're dealing with the sand, so we have no cohesion, right?
Right.
So we very quickly get rid of that term.
Oh, I just don't remember.
What else we know is real easy and quick in this one?
What is C if it's?
D sub F is 1,
What is C if it's?
and Q they gave us,
That'd be
right?
given.
Plus
It'd be
1/2.
DSF, sorry.
We'll skip that for a second. B is equal to
1,
2. And in gamma, they gave us. Didn't even make us go to the table or anything. So the really only thing we're missing here is these gamma values. Where's this gamma value come from?
It's gamma's sat minus
Yeah.
Well, don't worry about what the value is, but where's this soil that this term is calculated for?
below the bearing.
It's right in here, right? It's down in here. The first one is the surcharge due to Q, so it's what's here. Now in this particular problem, they're the same thing. They could be different. Now the kicker is this is 1 meter in the ground, this is 2 meters wide, and the water table's 5 meters in the ground. Do I need to worry about buoyant unit weights?
No, because it's not submerged.
I don't know.
He doesn't like to be there.
You don't for the first one. Paul.
For this one, you mean?
Yeah,
Yeah, so that one definitely doesn't need this program right there.
but
Okay.
that's the wrong one.
Oh, I did the wrong one. The one I meant to do, not the one I did. There you go. What about the second one?
I think if it's more than twice the base or something like that,
That's
you don't
a
have
good
to
rule of
worry.
thumb. You know, this is gonna have a fair envelope's gonna be shaped about like that, so
Whoa.
this is gonna be about 2. This is gonna be about B, maybe a little more B.
So if it were on.
So we're still well above this water table.
I was right.
So I don't think you need this one either.
I thought it was 2B.
Or not to be.
That's to get the stresses down to 10%.
Okay.
That's to get the stresses down to 10% increase. So we're gonna put 18 in each one of those.
Now, if that
And-
had been
That's our
within,
answer.
I mean, that was the rule of thumb, right? But that's not in here.
They're not gonna give you a problem. They're either gonna give you 1 or 2 problems. They're gonna give you a problem with the water table right here,
Yep.
right here,
Yep.
or way down in the ground, which is what they just did here.
Yep.
They're not gonna give it to you anywhere in this region because then it gets real complicated real quick.
So if it was that middle case,
If it was this case right here,
it would be, you'd have
then
two.
this term would have the buoyant on it.
You'd have two, they'd have to give you two weight.
They should give you a gamma M and a gamma sat.
Yeah.
Or they could,
Correct.
they could use that trick nomenclature, just call it gamma, but you said just assume that it is.
Yeah,
Correct. But if they're
you'd have
gonna
to
give
have more
you,
information.
in
That's
case
just
when
kind
you
of
have to
stuff
have
that pisses
both,
me off.
they're gonna have to give you both. And they're not gonna go that hardcore on you. It's gonna be, you're not gonna have a buoyant and weight in there anywhere.
Good to know.
They're not gonna be that difficult on you.
Great.
I don't believe.
I don't think it can. I do have a question though. If they did not give us the end values, they want to just use these 2 charts they'll give us,
They gotta give you a friction anchor.
and what about this bearing factor? What's the value we're going up to?
That's the value you get. All right, Q allowable.
also know the factor of safety.
You also know the factor of safety. They tell us we're gonna use a factor of safety of 3, 1260,
Gonna get that.
what is that? 420? Yeah, 420.
No, 15%. What is this?
I thought it was 20.
Is it?
He said 15 at the beginning.
Oh.
What's that?
15% of the. It's only 15% of
But the
whole
next
test.
closest one is 12%.
Dude, 15%'s a lot.
If the groundwater, they are gonna give it to you. If the groundwater level were to rise to the surface, so we'll get rid of that one. It gets all the way up to here.
Both have. They should
Both have
probably
point
not
weight.
stick a pile in there.
The ultimate bearing capacity would reduce to 956, 574, 630, 42. Now they didn't give gamma stat.
So.
There's a really quick method to do it when you I just don't remember exactly how. It's using unit of water multiplied.
The way the solution they provided was using this as saturated unit weight.
So they changed.
But that's not correct, right?
In real world.
In real world, this is gamma M, and gamma stat's gonna be like 21.
See, I will be working on that
How
for
did they
like
just
20
do
minutes.
that?
You
Yeah.
what now?
How did they do that? You can't use 18 as.
No, they can't. That's the way the solution that came with this showed.
That's
That's
the
the kind of
solution
stuff I
problem.
do.
Yeah, I mean,
I'll work on that
it's
for
a-
like
it's
20
a-
minutes doing that test.
Yeah.
Trying to
So
figure
let's
out
just
how to
depend
get
for
it.
It's a bad problem from that standpoint.
Yeah.
If they were gonna give you that scenario, they would have to give you a saturated unit weight. So you could take 9.81 off of it to get gamma buoyant.
So the answer is the same for both of them.
No, because you
No.
subtract 9.
No,
No,
you
you
subtract
You gotta start
9.81
subtracting gamma data.
from that. And put those values, and instead of 18, you're gonna have a little less than 9. So it's a little bit,
True FE probably won't be doing that, but they'll be
no,
getting us to that.
I don't see you guys doing that.
But I mean, even if they did do it right, probably they would give us 2 gamma values.
They would have to.
Yeah.
They would have to, or they can make you calculate gamma sat by giving you soil properties, but then that's interlacing 2 problems, and they're not gonna do that.
No.
Because if you screw up the
Really
calculated
awkward.
saturated weight, then you screw up the problem.
It's easy.
Do I get 200 points for my name on it?
What's that?
Like the SAT, you get 200 points to put your name on it.
Is that right?
Yeah.
Really?
Ah,
Yeah.
Rumor.
not bad.
That's lies, all lies.
It's kind of saying that you just,
Well, we'll
you're
just
going
see, I'll
to
leave
get
my name
the
off.
right answers.
Yeah, do perfect, leave your name off.
Also, you're gonna sacrifice your score and see if it works.
Let you guys know.
He's already accepted the grant, so we don't care.
Yeah.
He's become a PhD person anyway, he doesn't need to pass it.
Yeah. Are you gonna all the way, Austin?
All the.
Huh?
Are you going all the way?
You gonna go to third base there, Austin?
Everybody answer that.
What?
Unit weight of the soil behind and in front of the wall.
You will.
Yeah.
You're
You'll go all the way one day.
Put-
I say, I agree.
And the friction angle is 30 degrees. The active earth pressure coefficient is
What do we got here, Cliff?
Minus.
0.5,
What's going on in this situation?
0.3,
Tan squared.
0.2,
45.
so whatever the heck 1/6 is.
Tan squared 45 minus B is 2.
1.667.
Okay, hold on. I'm sorry, what is going on?
What is it? What am I doing?
We have a cliff, and that's all I know.
A cliff?
It looks like a cliff to me.
What is feet
Tan
farm
squared
again?
45 minus B over 2.
He wants the case
Tan
today.
squared 45 minus T over 2.
I'm not retaining
You
anything
guys are
anymore.
insane, I don't know how to do this.
Passive would be plus.
One of those you just gotta remember.
Yeah, I know that.
Remember 30 degrees, because that's what everybody likes to use for problems. 30 degrees, case of A is
Okay.
0.3, what's case of B?
Plus.
Race field, that's 3.
It's
It's
3.
again,
Yeah.
45 minus
Is that equating
15 is 30.
Yeah.
It's in
No,
there.
you're not.
Plus P
136.
plus P. For case of T, it's 3.
There it is.
So, I mean, everybody uses this value, so memorize those. And the problem, didn't ask yet, but what's K naught?
So definitely not K.
There's another one, y'all have all 3 of these values memorized. 1 minus sine phi.
Oh, yeah.
It's not given in here.
0.5.
I don't wanna focus on things that are not.
0.5. The active maximum earth pressure per length of wall is,
Where's a wall?
here's wall,
Oh, okay.
your wall,
Your wall.
your wall, see if it moves.
Well,
the next
if
question.
it's active,
Better not,
it
but.
is moving. If it's active, it is moving.
Yeah, so we're talking about the case-based condition.
It's parallel. We hope it's parallel.
Always be.
Max pressure
Gosh, I want a montage of teachers saying awesome things.
in KPA. And our choices are 486, 81, 36, 54. So maximum earth pressure per length of wall, so per length of the page.
Is this going based off of our case base and last problem?
Yes, it's all one problem, yes. So this is 0.3. So what's the pressure look like on the back of the wall? Triangle, right? What's a failure surface look like behind this wall? Failure surface.
From the toe
40,
to 45 plus B.
Yeah, okay, that was just a sidebar there. So there's the pressure. There's the pressure. So it's all these, so what's the maximum pressure?
1/2.
Brr.
The maximum pressure.
1/3.
You think-
Gallon.
I was starting to give you the equation, but.
You're wrong.
You were thinking of the.
Stop embarrassing yourself.
That's fine piece of the entire earth pressure.
Who thinks Chris is
To the
wrong?
bottom of the wall.
That 1/2,
That's
that
the-
1/2
we
case
want this
is
pressure right
where
here, right?
the area of that triangle.
We want that pressure,
That's
right?
the bottom.
Ka, gamma H, and the H is gonna be that.
I'm just gonna do a failure.
Gamma they gave us,
No, right?
base of A was 0.3,
So can I have my $75 back?
18,
Can I get that?
3.
$35.
So what's that come out to be?
The credit card take the test. It costs $75 to take the
does
test.
that
We're
mean-
getting a tuition
No,
waiver.
Oh,
Fee
it's only
waiver.
75. More than that.
154.
Is it seriously?
Yeah, we don't pay anything.
Oh, yeah, yeah,
I thought
That's
this was
fair.
$75. The first one's $75.
First one's 75.
Why would they say pressure though?
I asked Barry.
Yeah, why did they say?
So that's the
Why is-
maximum
why is
pressure.
this, I mean, this is a force, why is it still called not?
This is not a force, this is a pressure.
I mean, the other one, pH. Why is it
Sure,
called
it is.
pressure? Not force, if it's in pounds per foot. Oh, and you can just from each other.
What's the max pressure in KPA?
0.3 times 18 times 3 is not
Gamma's K
What I'm saying is, why is it?
0.3 times 18.
Yeah, that looks wrong.
Lateral force.
Units,
Per meter cubed.
Well, this is the pressure, and we turn it into a force when we do our analysis. When we do our analysis, we turn it into a force. What's the maximum passive earth pressure?
That was a pretty cool.
Yeah, that's not
Yeah,
good.
It's 16.2.
Yeah.
Maximum.
Quit embarrassing yourself.
Were they asking for?
18.
I tried to stop you.
We don't have a check. That's not one of the answers.
Did they ask for vertical or horizontal? Was it horizontal?
Is that 48.6 or 486?
I don't even
Answer.
think it's
Yep, 46, 81, 36, and 54.
Because 48.6 is the total giving you.
If you take-
down to the bottom of the wall.
That's a probable distractor problem.
It's
I just want to use that as much as possible.
plausible to stretch.
18 times 3 times 0.3 is 16.2.
54 would be the vertical pressure at that point then.
turn signal. Probably.
Yeah, the problem, the solution they had, they actually calculated it down here.
It's still not 54.
Was 9.
Well, I know, it's.
9 times 18 times 0.3.
It's 48.6.
I thought you had to.
9, 18
Extend
times
it a
9
little
times
longer.
3.
Keep going.
Oh.
Let's solve for 54.
Sorry. Now, the problem with that is, is the soil pressure on this side is canceling out the increase in soil pressure on this side.
Yeah.
So
So
the
it's-
problem
Wouldn't have to be.
should have been, this is the maximum pressure. They should have maybe phrased it, what's the maximum pressure at the ground surface?
So a lot of these problems.
That, the pressure on the left side of the wall would completely cancel out, would it?
No.
Everything
You
below.
still have a solid
Is this
wall.
large?
You'd still have this
Yeah,
rectangle.
right now. Okay, good.
So the actual,
48.
well, I guess the maximum pressure would still be the same down there.
So where's?
Interesting.
I hope it's 4.
That is true. That is true. This is a constant down through here.
So they messed
Yeah.
up.
So
So it's.
it is still
Another
correct.
bad problem.
It's not a bad problem. That is correct.
So I'm still
No,
at
I still-
No, that's still a
It's
bad
still
problem.
You still have a bad answer.
Oh, no, not yet. This is still the right answer. I mean,
Of course not.
that's the right answer.
Yeah, 16.1.
The 9 would, so it is, it is still wrong.
Good problem.
Still a bad
Bad
problem.
problem.
Still a bad problem.
4 times 3 is 1.
I think-
What's the active
It's
So this
earth
is
force per length
I thought it was
of the
48.
wall?
How do you get 40?
Oop.
0.3 times 18 times 9 is 48.6. What is
But
the
I
actual
thought
answer?
it was times 3.
The answer is 0.3 times 18 times 3.
Okay, so it's 16.2.
Correct.
That answer is not up there.
Actually,
It's a bad
18.
problem.
Did you write 81
just like the one
instead of 18?
It's 1/3, not 0.3, which is weird.
So I think we could just all walk away from this problem and agree it never happened.
We've got other earth pressure problems we've got that are much more
What's
basic.
1/3?
What's the location of the active earth force above the base?
Case A is not 1/3.
What's the location of active earth pressure above the base?
It'd be 3 feet from the base.
One third the height, right? Passive.
Wait, what's the name of that? The active earth pressure?
Yes.
Isn't that a force though? It's a third? Isn't it
Um,
the sum of all those?
where is the location of it if we
The
turn
sum,
it into a force?
the location is a third.
Yeah.
Oh, okay. Where is the location of the active earth pressure? As in what?
What did actually be lower for
Is it
considering that
horizontal
the
ground?
rectangle part of the ball?
You know,
Yeah.
most people
Well,
don't know
yeah.
how to be, but it do.
Like I said, but this is a bad problem. We need to have a problem that doesn't have this sheet pile wall under there. That's misleading for everybody.
We done.
What's that?
Dog.
So you had
I was
two
looking at him
balls.
before he looked at me. He was looking somewhere else. He goes,
Yeah,
They
but you
didn't
got
tell
counteracting pressures on this side. Now, if you didn't take that into account, maybe that would be
he
true.
looked at me
You
like,
didn't take that into account. Let's go here and see if there's some good ones here.
Effie,
Discipline review. That doesn't sound.
wow, that looks evil. Oh my God.
Yeah, you got them
It's
copies.
like the reverse.
It does look bad.
You remember
Sheet
Matilda,
pile
that
question.
torture
Yeah,
closet? That book reminds me of
That's what that
that.
looks like.
It's so random to think of.
They called it the choking.
Joking.
It's the hazing process at Virginia Tech.
Have fun, Austin. It's not like, yeah, I gotta
Yeah, active earth pressure.
go. Yeah.
Joking
About
on
to put
everybody.
some vertical earth pressures on my bed.
I'm trying to find another retaining wall problem real quick here.
Think.
Should probably turn the camera off. On.
Hey,
This is a better problem than you might actually see.
Garbage, anybody else? Anybody else?
All right, one more problem and then I gotta go.
We'll do one more pressure problem and then, because that's the one, that's more easy. And then,
One more life.
One more of everything that.
all right, let's go.
I thought about taking that out too.
This is a little better for you guys. This is similar.
Yeah, did they cover?
He's gonna dumb it down for us. One
I was gonna
more.
listen to Kyle, but he's
Make you
gone.
feel better.
Hey, there's a wall this time. Oh.
Hey, so good.
And we'll even do English units too.
American.
I'm American.
American units, yeah, that's right. Sorry.
Now I wish that that came
The retaining wall shown is 8 feet high.
We shall substitute.
Retaining wall shown is 8 feet high and retains a clean sand
Good dirty sand.
for which the unit weight is 120 pounds per cubic foot.
So you can't make
And
a
P equals 32 degrees. Calculate the active earth pressure at the base of the wall.
8 times 120 times.
All right.
Doesn't tell us.
That's K.
The retaining wall, so which way, what do you think it is? KA, KP, K, no?
Usually, yeah.
A.
Exactly.
Real quick, can you go through the differences?
Case of A,
Case of
A,
A
moves
goes
away.
away,
I can,
so
I can.
KT goes
Gamma
away.
M,
Just remember
or the
A,
gamma?
away.
Why would it go over towards?
Smack that bitch.
Why would it go
So
towards-
what's case of A for 32 degrees?
why would it go towards that?
I don't know, you told us the one for 30.
And squared, 45 minus 32.
Do it on the boat.
So underneath like slips and it would.
Memorize.
Times
So that
8
one.
feet for the height, times 120
The,
pounds per cubic foot,
K value.
and ends up being 295 pounds per foot squared. So that's the pressure, the maximum pressure at the base of the wall. Calculate the total earth force on the wall. Now's when you go.
1/2 KA times H squared. Gamma.
1/2 times K, the K factor, which is the case is active, case of A. Height of the wall times the weight of soil. And
So that's the maximum.
so this is piece of A. So we've got this force here. I do this to the wrong place. This is that piece of A force, 1/3 of the height up from the base. So that piece of A, we'll let me again. So that is that value right there. Calculate the overturning moment per linear foot of the wall due to the active earth pressure. So what's the overturning moment?
So I'll take a
Piece of A
moment.
times
Moment
20 degrees.
from the
Moment
bottom.
arm.
So
Think the
we're
moment about the
taking about the toe.
Ooh.
Piece of A.
So it's,
PA
Yeah.
times H over 3.
yep. Equals 0.
Piece of A times H over 3.
Minus the weight of the wall.
Yeah, minus.
It just asked what was the overturning moment.
Okay.
It's just.
Overturning moment,
So we don't care if it'll stay there, just
right?
it's pushing on it. Gotcha.
Moment overturning. That's nice and simple,
Like it.
huh? You wanted the movement conditions again.
You wanted that?
You
Did
did.
you want about how,
No, it's fine. I'll take KA as gospel.
if we got a wall that's not constrained at the top, you can move. Moves away from the soil, case of A, it's active.
Okay.
If the wall moves into the soil, it's case of P, passive.
I mean, I get that, but why would a wall move into the soil? Is there water on the other side? or is it-
Maybe there's a bridge right here.
You'd have
Like the
failure.
research we're working on right now.
Oh, yeah, it's fully.
There's a bridge right here and it
integrated.
expands due to thermal pressures, due to thermal stresses.
Ah.
It's gonna push on here.
Or if you have failure on
Or, we've got a retaining wall and we've got soil in front of it.
Stop this.
When the wall moves, we generate case of P right here.
What if you physically put in a tie back that has too much force?